Building and Environment Book Prepare Book, Hammad Sayyad Al-Khayari Building and Environment Table of Contents Chapter 1, Introduction to Building and Environment, 5 Definition and Importance, 5 Historical Context, 6 Chapter 2, Sustainable Design Principles. 13 Concepts of Sustainability in Architecture, 13 Chapter 3, Site Analysis and Planning, 19 Site Selection Criteria, 19 Chapter 4, Building Materials and Technology. 34 Chapter 5, Energy Efficiency in Buildings, 43 Chapter 6, Indoor Environmental Quality, 57 Chapter 7, Water Management in Building Design, 92 Chapter 8, Waste Management and Recycling in Construction, 103 Chapter 9 Climate Responsive Architecture, 109 Chapter 10, Urban Planning and Environmental Impact, 116 Chapter 11, Future Directions in Building and Environmental Design, 141 References. 152 Table of Figure 1 Building, 11 Figure 2 Green Building Design, 15 Figure 3 Smart Building, 41 Figure 4 Building Energy Management Systems, 50 Figure 5 CIM Connecting to a Building's Network, 52 Figure 6 BMS Generate Alerts, Designate Actions, Exchange Images, and Document Progress. 53 Figure 7 Schematic Overview of 2D Nanostructured Materials and Different Types of Heterostructures with 0D, 1D, 2D, and 3D Materials Used for Gas Sensing Applications. Reproduced with permission. 78 Figure 8 A Smart Ventilation System for Maximizing Indoor Air Quality, IAQ, Levels in Buildings, D, an illustration of the suggested electronics nose, ENOS, system architecture, A potential ENOS application in future smart buildings, B, and a crude concept design of smart air, C. Used by permission. 81 Figure 9 Urban Mining in Action, Examples of Material Reuse and Recycling, 106 Figure 10 The Effectiveness of Some Common Materials, 111 Figure 11 Summer Cooling, 112 Figure 12 Winter Heating, 112 Figure 13 Build Environment. 115 Figure 14 Torre Reforma by Benjamin Romano, Mexico City, Mexico, 121 Figure 15 Albion District Library by Perkins and Will, Toronto, Canada, 122 Figure 16 Transocean ICA Building by and Arquitectos, Santiago de Chile, Chile, 123 Figure 17 Floating School by Conel Adeyemi, Lagos, Nigeria, 124 Figure 18 Innovative Home by Joe Osiato, Accra, Ghana, 125 Figure 19 Eastgate Center by Mick Pierce and Arup Associates, Harare, Zimbabwe 126 Figure 20 Shanghai Tower by Gensler, Shanghai, China, 127 Figure 21 Asia Square by Denton Corker Marshall, Singapore, 128 Figure 22 Tokyo Toranomon Global Square by Nihonseki Inc., Tokyo, Japan. 129 Figure 23 Marco Polo Tower by Benisch Architekten, Hamburg, Germany, 130 Figure 24 Copenhill by Bjarke Ingels Group, Copenhagen, Denmark, 131 Figure 25 The Edge by PLP Architecture, Amsterdam, the Netherlands, 132 Figure 26 Pixel Building by Decibel Architecture, Melbourne, Australia, 133 Figure 27 French Polynesia Cultural Centre by Park Architects, Papeete, French Polynesia. 134 Figure 28 International House by Zans, Sydney, Australia, 135 Table Content Table 1 Common Indoor Pollutants and Their Effects on Human Health, 62 Table 2 Indoor Air Quality Guidelines for Major Indoor Air Pollutants, 71 Table 3 Building Related Diseases. 72 Table 4 summarizes the type of waste, legal classification, anonymous, 2020, 103 Construction and Environment, an all-inclusive guide introduction overview of the environment and buildings. This guide examines the complex interactions between human life, health, and sustainability and the built environment. Goals and scope. The book's objective is to serve as an all-inclusive reference for construction and environmental professionals, students, and legislators. The intended readership for this work includes policymakers, architects, urban planners, environmental scientists, and students studying related subjects. Acknowledgements. Special thanks are extended to professionals and specialists whose ideas, experiences, and case studies enhance the information in this book. Abstract. Construction and Environment, an all-inclusive guide offers a thorough analysis of the complex connections that exist between sustainability, human health, and built environments. This guide, which is intended for professionals in the construction and environmental fields as well as students and policymakers, is an essential tool for comprehending the complex relationships that characterize modern construction processes. The built environment is examined in the book's opening chapters, emphasizing both its significant influence on a variety of communities and its critical role in addressing societal demands. It highlights the need for moral frameworks in planning and design and promotes just solutions that take the needs of underrepresented groups into account. By using an interdisciplinary approach, the book makes connections between ideas in ecology, architecture, social science, and public policy to provide readers a comprehensive understanding of how the built environment affects people's health and well-being. Principles of Sustainable Design. The incorporation of cutting-edge technology like BIM and smart building systems, water management plans, waste minimization methods, and strategies for reducing the urban heat island effect are just a few of the many topics that are discussed. In addition, case studies of well-known green buildings from around the globe are included in the guide to highlight effective sustainable construction techniques that improve both environmental quality and occupant pleasure. The book's last chapters examine how building and urban planning should go in the future, highlighting how urgent it is to address climate change and promote resilient design in the face of harsh weather. The goal of this handbook is to inspire the next generation of construction methods that prioritize social fairness, environmental preservation, and sustainable development by promoting community engagement and collaborative approaches to policy formulation. Overall, Construction and Environment, an all-inclusive guide emphasizes the vital role that sustainable practices play in promoting a healthy planet and is an essential resource for anybody attempting to manage the complexity of construction in a modern setting. Chapter 1, Introduction to Building and Environment. Definition and Importance. The facilities and structures created by humans that serve as physical backdrops for human activity are referred to as the built environment. It is crucial to meeting society's fundamental needs, which include places to live, work, learn, travel, and amuse oneself. A more equitable society can be achieved through the built environment's ability to meet the needs of various people and groups. But traditional methods of constructing and planning the built environment have frequently disregarded the requirements of numerous groups. For example, 863 million people, or one-third of all urban dwellers in developing nations, live in slums and struggle with issues including poverty, poor housing, and inadequate services. Built environments have a detrimental impact on people's physical, mental, and emotional well-being even in more developed nations. Minorities, those with disabilities, and those with low socioeconomic level, SES. Equity can be promoted or inhibited in a built environment project in a number of ways across its lifetime, including during commissioning, planning, design, building, obtaining materials, and day-to-day use. These injustices cannot be ignored, even if the negative effects of the built environment on communities are unintentional outcomes. The needs of other groups may not be met by the design, construction, or operation of built environments, and the variations in human needs and behaviors in built environments may be too great to be taken into account completely. Some groups may suffer harm by traits that satisfy them, as these differences might even be contradictory. Older people prefer greater interior temperatures when they're indoors, but younger people prefer lower interior temperatures. When limited resources, such as time and money, are taken into account during the built environment's life cycle, it becomes even more difficult to take into account the changing needs of occupants and users. It is therefore a difficult challenge to design for the widest possible range of users of the built environment while taking into account the distinctions between several groups. This calls for acknowledging that certain groups may profit more than others from the features of the built environment, and that, In general, relative differences favor the more disadvantaged or less capable groups. Equity-based approach. A. Kokoskis, 2020. The phrase built environment refers to circumstances that have been created by humans and is frequently used in the fields of public health, anthropology, urban planning, architecture, and landscape architecture. These carefully designed areas were made to satisfy human needs and desires while also serving as a backdrop for human activities. The phrase can be used to describe a wide range of elements, such as the customarily connected cities, farms, dammed rivers, public transportation, open space, and public infrastructure, as well as more abstract elements like tamed animals and wildlife management. Physical elements make up the constructed environment. On the other hand, research on the built environment frequently emphasizes the relationship between spatial arrangement and social outcomes. In addition to more intangible facets of society like socioeconomic inequality and health, it affects the environment and the actual movements and operations of civilization. Scholarship on housing and segregation, physical activity, food access, climate change, and environmental racism benefits from a variety of built environment factors. Historical context. The phrase built environment was first used in the 1980s and gained popularity in the 1990s, setting the idea apart from the purportedly unbuilt environment. The phrase refers to an interdisciplinary concept that encompasses a wide range of areas and has been acknowledged as such since classical antiquity, if not earlier. The development of the built environment into its current state has been possible to be investigated through the study of anthropology. The built environment's borders are pushed into new places when people are able to go outside of urban centers and other areas where it is already noticeable. Transportation made it possible for the built environment to spread and grow, even though there are other elements that also affect it, such as improvements in agriculture or architecture. Prior to the Industrial Revolution about 12,000 years ago, agriculture, the practice of cultivating land to raise crops and livestock for both food and products, was initially developed. The Neolithic Revolution, another name for this transition, marked the start of the practice of promoting long-term habitation and modifying the terrain to cultivate crops and raise livestock. This could be considered the inception of the constructed environment, the first attempt to alter the surrounding landscape in a lasting way to suit human requirements. Around 7500 BCE, settlements began to form, strewn around areas of fertile soil suitable for farming. Making sure that fundamental necessities were being satisfied was a top priority in these early settlements. Even if it was not as vast as it is now, the constructed environment was starting to be developed with the construction of structures, roads, farms, domestication of plants and animals, etc. These smaller towns and villages developed into larger ones throughout the course of the following several millennia, with trade, culture, education, and economy serving as the primary drivers. Cities had to expand to accommodate more people as well as change from prioritizing survival needs to comfort and desires as cities grew. Since many people still lack access to basic necessities in today's world, this idea of a shift makes sense given how society has evolved over time. As a result of this change, these cities' constructed environments grew larger to accommodate the expanding needs of their populations. Revolution Industrial suggested street drawing. From 1914, the Industrial Revolution saw the peak of city growth as a result of the increased demand for labor brought about by the expansion of factories. Between the 1880s and the early 1900s, American cities expanded quickly. Due to this demand, people moved from farms to cities, necessitating the expansion of municipal infrastructure and causing a population explosion. Due to the quick population expansion in cities, there are now concerns about traffic congestion, pollution, noise pollution, hygienic conditions, small living spaces, etc. To address these problems, the built environment was made better by prioritizing the construction of public transit, trolleys, cable cars, and subways. During the Industrial Revolution, the City Beautiful movement served as an illustration of this. The chaos and poor living conditions in industrial cities gave rise to the City Beautiful movement in the 1890s. Public areas, municipal centers, enhanced traffic, and greater sanitation were all advocated by the movement. The intention behind these upgrades was to increase their profitability while also enhancing the quality of life for their occupants. Although it lost favor over time, the City Beautiful movement brought about a number of urban reforms. The movement placed a strong emphasis on public transit, city planning, civic education, and municipal cleaning. From the post-industrial revolution until the present, the manufacture of steel, chemicals, and gasoline enabled new improvements that made autos and train travel more accessible to the general public. Henry Ford's innovations in assembly line manufacturing made cars more affordable for the masses in the 1920s. In order to handle this unprecedented surge in personal mobility, new infrastructure was constructed. In 1956, motorways were initially constructed in an effort to get rid of dangerous roads, congested areas, and inadequate routes. The development of interstate highways and motorways made it easier and more feasible for people to travel outside of their city. This altered the structure of the built environment and made transit easier than it had ever been. As automobiles gained popularity, communities began to build new roadways to accommodate them. Additionally, railway lines were constructed to connect previously disconnected places for the purpose of both public and freight transit. In addition to the transportation of products, these modifications caused a city's boundaries to start expanding. The development of suburbs was made possible by the widespread use of automobiles and public transportation, which allowed working people to travel great distances for their daily commutes to work. The borders of cities became less distinct as more people chose to live in suburban areas. Daily activities that had previously only taken place within walking distance were now spread out over a large area thanks to the usage of vehicles and public transport. The constructed environment was able to keep growing because of the improved accessibility. The interdisciplinary area that includes the design, building, management, and use of human-made physical influence as an interconnected whole is currently referred to as the built environment. The idea also takes into account how these constructed environment components interact with human activity over time, rather of focusing on a single component acting alone or only at one point in time. These components work in concert through the multiplier effect. The built environment is a broad umbrella that encompasses a variety of disciplines, including economics, law, public policy, sociology, anthropology, public health, management, geography, design, engineering, technology, and environmental sustainability. Some academics in the current day believe that the built environment is everything and that the natural environment is extinct. This argument is based on the notion that the built environment includes both managed and controlled elements as well as those that are constructed, staged, or curated. What we now refer to as nature is really nothing more than an object inserted into a setting designed to satisfy human need and will. With the help of this resource, people can take in the beauty and wonder of nature without having to compromise their daily routine. One could argue that the seemingly natural, pedestal-bound forests and wildlife parks are actually created and permitted to exist for the benefit of humankind. Human contact has permanently altered the world. The list of crimes against wildlife includes hunting, harvesting, driving it to the verge of extinction, and altering it to suit human demands. This argument counters the claim that nature's forests, oceans, wildlife, and other features are separate entities, and that the built environment is limited to what has been created. Sussman, 2024, Interrelationship between buildings and environment. It is evident that the building and its surroundings are intricately linked. Buildings are more than just structures, they engage in a variety of constant interactions with their surroundings. The salient points are as follows. Buildings have a major impact on climate change by contributing significantly to CO2 emissions. A building's environmental impact can be significantly decreased by using sustainable materials and design. Enhancing building performance and comfort requires long-term care and consideration of the local context. It is imperative that the built environment change quickly. Through the design of ecologically conscious and energy-efficient buildings, we can guarantee a healthy future for all while meeting our climate commitments, especially the 1.5C target. This entails choosing eco-friendly materials, maximizing energy efficiency, and taking the surrounding environment into account while designing these structures. I'm Pam Hutter, the principal of the Chicago, Illinois-based firm Hutter Architects. With a background in creative design and project management, I concentrate on making structures that are not only aesthetically pleasing and useful, but also environmentally friendly and sustainable. Let's now explore more closely at the details of the interactions between buildings and the surroundings. Recognizing the built environment, the surroundings created by humans that serve as the backdrop for human activities are collectively referred to as the built environment. Buildings, parks, highways, bridges, and other infrastructure are included in this. All of it is, in essence, human construction intended to produce a habitable environment. Products that make up the built environment, these are the supplies and tools used in building, like steel, glass, and bricks. Interiors, this refers to the plan and arrangement of a building's interior areas, such as public areas, offices, and residences. Frameworks, these are the real structures from single-family homes to skyscrapers and their physical manifestations. Landscapes, this category includes outdoor areas such as gardens, parks, and green roofs. Cities, combined urban areas of all the smaller parts, forming an intricate web of residential and commercial places. Regions, broader areas made up of several cities and towns. Earth, the world around us that is influenced by and engages with the constructed environment. Environments made by humans' people's wants are taken into account when designing the built environment. This entails setting up areas for work and play as well as for shelter and transit. Our natural environment can, however, be greatly impacted by the way we plan and construct these environments. For example, every year, the construction and maintenance of buildings accounts for about 27% of the world's carbon emissions. This covers the emissions produced by lighting, air conditioning, heating, and other building functions. Infrastructure, the vital services and systems that sustain the built environment are included in infrastructure. This includes airports, railroads, bridges, and roads make up the transportation networks. Water supply, sewage, electricity, and telecommunications are examples of utilities. Public services include government buildings, hospitals, and schools. Sufficient infrastructure is essential to the efficient operation of cities and regions. It is essential to sustainability as well. Efficient public transportation systems have the potential to minimize carbon emissions by reducing the dependence on individual vehicles. The mutually beneficial partnership infrastructure and buildings interact with their surroundings, they are not solitary entities. For instance, energy efficiently built green buildings can lower operating emissions and help meet climate targets. As the paper notes, making use of natural light and views can enhance tenant well-being and lessen the demand for artificial lighting, saving energy. To create sustainable and comfortable areas, buildings, and the environment must coexist in a symbiotic connection. We may create a functional and environmentally friendly future by comprehending and maximizing this relationship. Park, 2022, Figure 1 Building Current Trends and Future Directions. The creation of low-carbon buildings, LCBs, has accelerated recently due to the intensification of climate change, and building information modeling, BIM, is thought to be the most promising route. The potential of BIM to help LCBs reach their goal may be hampered by the lack of systematic integration, review, and analysis of research in the field of BIM for LCBs. As a result, this paper examines the state of BIM research for LCBs as well as potential future research areas. The strategy used for the literature review was a hybrid one that combined quantitative and qualitative analysis. Firstly, 158 studies that were found through a search of the Web of Science core collection underwent a quantitative bibliometric analysis. The most prestigious organizations, publications, research projects, and search terms were determined. The terms that were most frequently used were digital technologies, DTs, design, construction, life cycle assessment, LCA, BIM, and integration. In the second step, 117 carefully chosen studies were subjected to a systematic qualitative analysis in order to determine the study focus of various stages, such as design, construction, operation, and demolition, of BIM for LCBs. The findings indicated that while there were comparatively few research concentrating on BIM for LCBs throughout the operation and demolition stages, the majority of studies relevant to BIM for LCBs focused on the design stage and the complete life cycle perspective. Research at the moment is concentrated on how the newest techniques and technology can be applied to assist in lowering carbon dioxide emissions throughout the life cycle. BIM in conjunction with DTs and BIM LCA. Finally, a thorough discussion is had of the difficulties and opportunities associated with combining BIM with LCA and new DTs for LCBs. Future research trends are suggested for 5 themes, including BIM-based interdisciplinary collaboration and testing and enhancing the BIM integrated sustainability calculation models. For academics who wish to focus on this area, this report identifies potential research directions and hotspots in the subject and provides a strong foundation. The study's conclusions may be used as a useful guide by LCB practitioners to better grasp the potential of BIM for their organization and to make the most of it in order to achieve their objectives. Liu, 2023, Chapter 2, Sustainable Design Principles in Architecture. Sustainability is a crucial field that combines social justice, economic viability, and environmental care. The fundamental ideas and procedures that support sustainable design practices will be covered in detail in this chapter, emphasizing the significance of designing environments that are not only practical and visually beautiful but also ecologically conscious and culturally appropriate. Concepts of sustainability in architecture. The term sustainable architecture refers to a broad category of sustainable design. These architectural examples utilize energy consumption into the building design to lower each structure's carbon footprint. Basically, by using natural materials, sustainable design raises your level of living while using less energy. Green architects hold certifications from the Leadership in Energy and Environmental Design, or LEED, as well as BREEAM. These certifications go into great detail about what is required to evaluate sustainability indicators. For a green building to be considered sustainable development, it is imperative that it adhere to the BREEAM requirements. Samuel, 2024, 2.2 Green Building Standards, LEED, BREEAM, etc. Buildings affect the environment greatly, both directly and indirectly. Buildings consume energy, water, and raw materials during their construction, occupation, refurbishment, repurposing, and demolition. They also produce trash and release potentially hazardous emissions into the atmosphere. Due to these facts, green building standards, certifications, and rating systems were developed with the goal of using sustainable design to lessen the negative environmental effects of buildings. The introduction of the Building Research Establishment's Environmental Assessment Method, BREEAM, the world's first green building grading system, intensified the drive towards sustainable design. Following suit, the United States Green Building Council, USC, created and published guidelines with the goal of enhancing building environmental performance through the use of its Leadership in Energy and Environmental Design, LEED, rating system for new construction. LEED is becoming more and more well known, and it currently incorporates rating systems for neighborhoods, interiors, and existing structures. The Green Building Initiative, GBI, which was established to support the National Association of Home Builders, NAHB, in promoting its green building guidelines for residential structures, is one of the organizations that also reacted to the increasing interest in and demand for sustainable design. Green globes were first created for Canada, but GBI assisted in bringing them to the United States. Although they are adapted to their own national priorities and requirements, other rating systems that were inspired by these early programs have been developed. These systems aim to address more comprehensive sustainability issues, such as net zero energy, living, regenerative, and restorative building, by going beyond the constraints of current policy and building practices. Since the 1980s, there have been more and more green product standards available on the market. when worries about product toxicity and its effects on children's health and indoor environmental quality, IEQ, first grew, several green product standards were created. The amount and variety of green product standards and certifications are expanding in the modern era as evidence supports growing worries about resource depletion and climate change. The scope of environmental concerns and the effects of items during production, usage, and recycling has also increased. Although there isn't yet a consensus on what constitutes a green product, these goods are meant to live up to promises that they are better for the environment and meet certain requirements. The market is flooded with standards, grading systems, and certification initiatives that serve to direct, illustrate, and record attempts to produce high-performance, sustainable buildings. Globally, there are hundreds of green product certifications, with many of them being used in the United States, and the list keeps growing. Globally, there are also green building rating systems in operation. These systems differ in how they go about things. Some define requirements and optional credits, others adopt a prescriptive strategy, and still others propose performance-based standards that can be satisfied in various ways for various goods and project kinds. As such, figuring out which standards, certifications, and rating systems are most reliable and relevant for a given project can be difficult and time-consuming. This page offers definitions for several often used words, a summary of the most well-known green building product standards, and an overview of the building rating and certification schemes now in use, with a focus on their differences and some considerations for choosing them. Figure 2 Green Building Design. A construction guidelines. A standard is a collection of rules and specifications that can be used to evaluate a product. ANSI, ASTM, and OSHRI are among the organizations that use consensus methods to set common standards pertaining to construction practices. The International Standards Organization, ISO, which creates global standards that frequently become laws or serve as the foundation for industry norms, supports the governance of standards and certifications. According to ISO, a standard is a document that is created by consensus and authorized by an established body that specifies common and repeated use as guidelines, standards, or characteristics for actions or their outcomes. Standards contain requirements that can be performance-based, specifying expected outcomes, or prescriptive, defining means of achievement. Standards based on consensus, such as those created by an official, voluntary consensus process that is represented by an open and due process, have instant public acceptance, governmental backing, and global clout. The National Technology Transfer and Advancement Act, NTAA, mandates that government agencies accept voluntary, private sector standards that are already in place rather than developing proprietary, non-consensus standards. Green labels. In order to raise the bar for building design and construction to new heights of sustainability and performance, green building regulations are still being established and enacted both domestically and internationally. There are two primary types of codes, performance and prescriptive, with outcome-based codes emerging as a third option. A prescriptive path is a quick, firm, and methodical way to comply with the code. Tables quantify the levels of stringency that materials and equipment must meet. Performance-based codes are not meant to fulfill specifications for specific building elements, rather, they are meant to accomplish specific goals. Tables quantify the levels of stringency that materials and equipment must meet. Performance-based codes are not meant to fulfill specifications for specific building elements, rather, they are meant to accomplish specific goals. To ensure that the finished building operates at the specified energy use level, outcome-based codes, for instance, set a target energy use level and provide for measurement and reporting of energy consumption. Part 11 of the California Building Standards Code is the California Green Building Standards Code, CAL Green Code, which was the nation's first statewide green building code. The goal of Cal Green is to conserve water while promoting affordable, eco-friendly, and healthier places to work and live. By promoting sustainable construction practices in the following areas and improving building design and construction through the use of building concepts with a reduced negative or positive environmental impact, CAL Green seeks to improve public health, safety, and welfare. Organizing and creating energy effectiveness, water saving and efficiency, preservation of materials and effective use of resources, quality of the environment. Vieira, 2023, Life Cycle Assessment, LCA, in building design. A building's entire environmental footprint, including factors like energy use, potential for global warming, habitat loss, resource depletion, and hazardous emissions, can be conceptualized as the result of an LCA. One of the best tools for assessing buildings and designs is life cycle assessment, LCA. In order to assist architects in comprehending and applying life cycle assessment, LCA, methodology as a component of the design process, this article offers explicit guidelines that are tailored exclusively to the architectural profession. It offers a set of suggested principles for the execution of whole building life cycle assessments, LCAs, and identifies scenarios for their application in the design phase. 2023, Resilient Design Strategies. Strategies for resilient design. Resilience isn't a single fix or method of construction. It is important to see resilience through a variety of lenses, and this means that developing proactive responses to disruptive events is necessary. To put it another way, a thorough rethinking of the built environment is necessary for resilient design. The following is a compilation of useful tactics to enhance resilience, keeping in mind that every project is unique. Adaptability at the building level. Buildings should be designed and built to endure harsh weather conditions, such strong storms. It is best to locate critical systems in places that are immune to flooding and other adverse weather conditions. A region's behavior can be better understood by looking at historical climatic records. But designs also need to take future weather patterns into account. Create structures that can be inhabited even in the event of a protracted power outage or a disruption in the supply of heating fuel. Passive heating and cooling methods and other energy-saving strategies can help achieve this. Create long-lasting structures with features like impact-resistant windows, waterproof interior coatings, and rain screens. Encourage the use of water-saving techniques like gray water recycling and rainwater collection. Find out whether materials or items will leak dangerous substances in the case of a fire or flood, and educate yourself about product hazards. Install backup water sources or emergency water storage. Install electrical systems that are redundant and have sufficient backup power for essential equipment and gadgets. Think about other options for handling human waste in situations where the municipal wastewater system is interfered with. Composting toilets and waterless urinals are two such. Adaptability at the local level. In order to control stormwater and lessen the heat island effect, use green roofs and rainwater collection systems. Roadways, bridges, and other physical infrastructure should be designed to accommodate rising stormwater flows. Put erosion management techniques into practice, especially those that blend in with the environment. Provide community spaces that serve as meeting spots in case of an emergency. Large buildings like schools provide the ideal setting for this. Essential utilities like electricity and water should be available in these locations. Adaptability at the local level. Tobias, 2024, Chapter 3, Site Analysis and Planning. Site Selection Criteria. The significance of choosing the ideal location for construction projects. An overview of how site selection affects project success. A building project's success can be greatly impacted by choosing the ideal site, which is a crucial choice. We explore the many facets of site selection in this extensive guide, providing insights into important factors including zoning laws and accessibility to transit networks to topography, environmental impact, and soil quality. We stress the value of taking a comprehensive approach while navigating these variables, taking into account market research, community connections, legal issues, and potential future growth. With the help of this book, you should be able to fully comprehend the nuances of site selection, laying the groundwork for a project that is both profitable and long-lasting. Highlight on location. Your project's key. The success of your construction project is greatly influenced by the site you choose. Think about being close to transport hubs as an essential component. Selecting a location that is easily accessible to ports, highways, and railroads helps expedite the delivery of equipment and building supplies, reducing expenses and averting delays. Accessibility for construction equipment and vehicles is equally important. Examine the site's roads to make sure they are suitable for heavy-duty vehicles. Additionally, take into account the availability of construction vehicle parking places on site, which will lessen logistical issues during the construction phase. Understanding zoning, easily navigating regulations. One of the most important aspects of choosing a site is navigating the intricate labyrinth of local zoning laws. Verify that the site selection complies with current zoning regulations, which specify acceptable land uses. By being aware of these rules, you can avoid expensive legal problems and delays in getting the required permits. Restrictions on land usage are a further important consideration. Look into any restrictions that may apply to the particular kind of construction you have in mind. For instance, restrictions on building height or architectural styles may apply in some places. It is possible to avoid later project modifications or redesigns by being aware of these limitations early on. Dirt matters. A basic understanding of soil. Knowing the soil composition and site quality is one of the most critical aspects in ensuring the stability and longevity of your building project. Conduct a complete soil test to assess factors such as drainage features, load-bearing capacity, and potential challenges like soft soil or expanding clay. The subsurface conditions should be considered before beginning any building project. Inadequate testing could lead to unforeseen difficulties like uneven settling or problems with the foundation. Seasonal variations can cause soil expansion and contraction in regions with expansive clay soil, which could affect the structural stability of your buildings. Invest in thorough soil testing to obtain priceless information that guides foundation design and building techniques adapted to the particular soil conditions. Recognizing topography. A construction site's suitability for your project is largely determined by its topography. Examine the land's elevation and slope carefully since they have an impact on foundation needs, water drainage, and the construction process as a whole. Slopes that are too steep for a building site could make excavation and foundation building more difficult. It might also have an effect on the project's final appearance and functionality. On the other hand, a site that is level or slightly slopes may be advantageous for accessibility and building efficiency. To design drainage systems that work, it is important to know how water will move over the property during rainy seasons. This helps to ensure that the structures won't be damaged by water during construction and also increases their long-term endurance. Effects on the environment. Assessing and reducing your project's environmental impact is a key component of a sustainable and ethical construction process. To find any ecological repercussions connected to the development site, do an environmental impact assessment. Think about the neighboring water features, delicate ecosystems, and the local flora and wildlife. Respect environmental laws and secure required permits to show that you are dedicated to using ethical building methods. This not only guarantees legal compliance but also enhances the project's overall environmental consciousness. Proactively demonstrate your commitment to environmental stewardship by putting erosion control tactics into practice and avoiding disturbances to nearby wildlife habitats. Using sustainable methods from the start can improve the project's reputation and may even help you get eco-friendly certifications. Infrastructure fundamentals. For a building project to be successful, reliable infrastructure and necessary utilities must be available. Examine the availability of gas, power, and water, making sure that these services fulfill the project's needs. Building delays and higher building expenses might result from inadequate utility access. Analyze the region's current infrastructure. A location with well-established infrastructure promises a more seamless construction process and is also a positive indicator for future development. Take into account the ability of the current utility networks, roads, and bridges to handle future growth or heightened demand. Expense factors. Although it may seem apparent, carefully examining the project's total expenditures is an aspect that needs to be paid close attention to. Aside from the land's purchase or lease, account for costs associated with site preparation, such as grading, excavation, and any required environmental cleanup. Long-term operating expenses are also taken into account when calculating costs. A site may seem reasonable at first, but unstated fees like property taxes, energy bills, and continuous upkeep can seriously affect how financially feasible the project is. A thorough budget that takes into consideration every possible expense, both one-time and recurring, facilitates improved financial planning and reduces risk. Additionally, it guarantees that your project will continue to be profitable once it is finished. Evaluation of risk. One of the most important steps in detecting and averting possible problems that can affect your building project is carrying out a comprehensive risk assessment. Recognizing the site's potential for natural disasters is essential. Taking these risks into consideration enables the implementation of suitable design and construction procedures, regardless of the area's susceptibility to earthquakes, floods, or other natural disasters. Investigating past site stability data also sheds light on any problems or difficulties that related projects in the region may have encountered in the past. This historical perspective helps you create plans to deal with or steer clear of possible problems, which makes your building project more resilient overall. Always be aware of your surroundings. Making educated decisions requires having a thorough understanding of the neighborhood's past, present, and future. Examine the neighborhood's growth potential because it has a direct impact on market trends and property values. An area that is growing is probably going to gain value over time, so your investment will pay off in the long run. Take into account the neighborhood's current facilities, infrastructure, and community services. Being close to medical facilities, retail establishments, and schools can greatly improve the desirability of your property. Keeping up with impending neighborhood projects also gives you a glimpse into possible rivalry and market saturation. Relations between the community and stakeholders. Although it is sometimes overlooked, developing strong relationships with stakeholders and the local community can have a big impact on how well your construction project turns out. Early in the planning process, interact with the community, get their input, and resolve any issues they may have. This open and cooperative approach cultivates goodwill and helps lessen possible resistance to your initiative. Keep the lines of communication open with local government representatives, citizens, and business owners to foster an environment that will support your construction endeavors. Legal aspects to take into account. It is necessary to actively navigate the legal landscape in order to provide a strong basis for your building project. It is essential to comprehend property rights and verify the chosen site's legal ownership. Any doubts regarding these elements could impede your construction project's development and result in legal issues. The settlement of any ongoing legal issues pertaining to the site is equally crucial. To guarantee an unhindered and transparent road for your construction project, this entails closely examining land titles, investigating previous transactions, and conferring with legal professionals. By addressing legal issues up front, one can reduce the likelihood of legal issues and any setbacks, which can facilitate a more seamless construction process. Future prospects for growth. When choosing a location strategically, one must actively consider future requirements and possible growth. Evaluate your project's growth potential and ascertain whether the selected location can support such expansion. To make sure that your long-term development objectives are compatible with the area, take into account the zoning and land use plans. Selecting a location that facilitates growth not only meets current requirements but also protects against the constraints of a stagnant setting. This innovative method gives your project more adaptability to meet shifting market demands and maintain its relevance in the rapidly changing construction industry. Availability to employees. The importance of accessibility for workers and proximity to labor markets is sometimes overlooked while choosing building sites. Make sure that the location is conveniently accessible and actively assess the commute options available to prospective employees. Examine the influence of public transit availability on hiring and retaining employees. In addition, it is imperative to proactively evaluate lodging alternatives for construction laborers. A consistent and competent staff can be attained by locating the site close to inexpensive housing or short-term accommodation choices. Investing in the accessibility of employees promotes a productive workplace and reduces the likelihood of delays brought on by a labor shortage. Regulatory acceptance. An important consideration when choosing a development location is navigating the regulatory environment. It becomes imperative to streamline the permitting procedure to prevent needless delays. It's important to get familiar with the federal, state, and municipal laws that regulate building projects. Planning to construction will go more smoothly if you are aware of the rules and deadlines for acquiring the required permissions. Furthermore, adherence to regulations goes beyond obtaining permits. Compliance with building, safety, and environmental requirements becomes essential to the outcome and viability of your project. It's crucial to keep up with changing rules if you want to continue to be compliant during the building process. In addition to displaying a dedication to moral and legal obligations, proactive regulatory approval management lowers the possibility of hiccups and expensive fines. Examination of the market. Doing a comprehensive market analysis is necessary to ensure that your building project is in line with both current demand and emerging trends. Determine whether the sort of construction in the area is in high demand. Gaining insight into industry trends and competition can help identify potential obstacles and opportunities. Take into account the region's economic characteristics, such as employment rates, industry developments, and population growth. Make active use of this data to predict market situations before, during, and after construction to customize your project to fit present and future requirements. To obtain in-depth market information, aggressively carry out feasibility studies and collaborate with regional real estate specialists. You can increase your project's viability and success rate by proactively matching it with market demands. Weather conditions. The local climate has a direct impact on construction, influencing project deadlines, materials, and construction techniques. Having a thorough awareness of the site's climate is essential to organizing and carrying out a construction project successfully. Take into account elements like seasonal fluctuations, precipitation patterns, and extremes in temperature. Severe weather conditions, such as hurricanes, or a lot of snowfall, can seriously interfere with building schedules and raise the possibility of structural damage. You can use building techniques and materials that are tolerant of the local environment by actively considering the climate. Furthermore, proactively create backup plans to deal with weather-related delays so that the project timeline is more dependable. Materials availability. Evaluating the accessibility of building materials in the area is a crucial factor that might affect budget and schedule. Look into if the resources you'll need for your project are easily available in the area. If there aren't enough supplies from local sources, take transportation costs into account. Being close to suppliers can simplify material delivery operations and cut down on potential delays and transportation costs. Furthermore, knowing the caliber and reliability of the materials that are readily available guarantees that your project will uphold strict building requirements. Establishing a dependable construction material supply chain reduces the possibility of material shortages, which can lead to delays in your project while also improving prices and efficiency. Site dimensions. The building site's dimensions and layout have a direct impact on your project's viability and effectiveness. Assist in making sure the site satisfies the spatial specifications outlined in your building plans. A site that is large enough actively prevents limitations during the construction phase, enabling an effective layout and best use of available space. Examine the site's shape, taking care to steer clear of any irregularities that could make construction more difficult. Regular, well-defined shapes actively encourage simple planning and construction, which lowers the possibility of last-minute changes to the design during the building stage. You provide the foundation for a construction process that actively maximizes efficiency and minimizes potential obstacles by thoroughly and actively assessing the site's size and shape. Safety and security. Security and safety should always come first when choosing a building site. Determine the necessary level of security for both the development and post-construction periods by analyzing the area's crime rates. Your investment is safeguarded, and stakeholder and employee safety is guaranteed, with a secure site. A secure working environment is facilitated by the implementation of complete safety measures, such as fencing, surveillance, and on-site security officers. By addressing safety issues early on, you lower the chance of mishaps, theft, and vandalism, protecting the project's construction site as well as the participants' health. Exit tactics: when choosing a construction site, planning for a clear departure path is a strategic aspect that is frequently disregarded. Consider future possibilities, such as selling or using the property for another purpose, and evaluate the site's long-term marketability to make sure it fits in with your investment objectives. Whether selling the property when it is finished or putting it to another use, an exit strategy offers a clear roadmap for leaving the project. It is important to comprehend the state of the industry and the possible demand in the future to make sure your exit strategy is informed and in line with your financial goals. Your investment planning will be improved and you will be better equipped to adjust to shifting market conditions if you include an exit strategy in the site selection process. The need of careful site selection in the complex world of building cannot be emphasized. Every component, from the complexities of soil composition to the accessibility of transportation networks, is vital to a project's success. As we get to the end of this investigation, it is clear that a comprehensive approach to site selection that takes community involvement, legal issues, and market analysis into account is crucial. By taking proactive measures to mitigate risks, complying with regulations, and keeping up with emerging trends, you can protect your investment and enhance the overall sustainability of your construction projects. I hope this guide will be a useful tool for you when you start your next project, helping you choose a location that will not only satisfy your current requirements but also pave. Karthik, 2024, Climate and Environmental Impact Assessment. Environmental Impact Assessments, EIA, and Strategic Environmental Assessments, SE, must be completed as part of planning and development procedures, especially for large-scale residential or commercial developments. These investigations ensure that the environmental implications of developments are fully understood and taken into account before any planning permission is granted. This handbook provides a comprehensive overview of the manner in which EIAs and SEs are involved in the development process, with a focus on their significance, methodology, and role in achieving sustainable development. Comprehending SE and EIA before decisions are made, the environmental implications of planned developments are identified and evaluated through the Environmental Impact Assessment, EIA, process. It addresses a broad spectrum of environmental aspects, such as cultural heritage, biodiversity, and the quality of the water, air, and soil. Large-scale projects that could have a substantial negative impact on the environment are often subject to the project-specific EIA process. Strategic Environmental Assessment, see this more comprehensive assessment assesses the environmental effects of suggested plans, programs, and policies, in contrast to the project-specific Environmental Impact Assessment, EIA. SEs are employed to incorporate environmental factors into the formulation and approval of strategic choices that direct upcoming development initiatives. The functions of SE and EIA in major projects. EIAs and SEs are essential for guaranteeing environmental sustainability and regulatory compliance for large-scale residential or commercial developments. These evaluations inform decision-making, by offering insightful data regarding the potential environmental effects of planned developments. EIAs and SEs assist decision-makers in thinking through alternate choices and mitigating measures. Prevent environmental damage. These evaluations assist in preventing or lessening adverse effects on the environment by detecting potential environmental consequences early in the planning phase. Encourage public participation. The public is given the opportunity to voice its opinions and concerns on the environmental effects of developments through public consultation processes, which are a feature of both SEs and EIAs. Promote sustainable development. EIAs and SEs help to accomplish sustainable development objectives by incorporating environmental factors into the planning and decision-making process. The procedure for EIAs. There are usually several important steps in the EIA process. Screening. Based on a project's size, nature, and possible environmental effects, it ascertains whether an EIA is necessary. Scoping. defines the main environmental concerns and the scope of the necessary assessment. Impact assessment examines the project's possible consequences on the environment, taking into account both good and negative outcomes. Mitigation suggested solutions to prevent, lessen, or offset harmful effects on the environment. Reporting prepares an environmental impact statement, EIS, and submits it to the entity that makes decisions, summarizing the results of the EIA. Review to make sure the EIS satisfies the necessary requirements and appropriately addresses any potential environmental implications, it is examined by the appropriate authorities. Making decisions, the body that makes decisions takes into account the EIS in addition to other. The C method. While it functions at a strategic level, the C process is comparable to the EIA. It includes establishing the background and goals, specifies the goals that the plan, program, or policy should accomplish in terms of the environment, society, and economy. Developing alternatives takes into account several approaches to achieving the goals with the least amount of negative environmental effects. Analyzing the effects considers each option's potential effects on the environment. Consultation inquires about opinions on the environmental report and the suggested strategy or program from the general public and interested parties. Monitoring puts in place a monitoring program to keep tabs on how the plan or program is affecting the environment and make sure mitigation measures are working. Important ecological aspects taken into account in an EIA. Biodiversity, this covers how local habitats, protected species, and flora and animals are affected. The evaluation considers the effects on biodiversity conservation as well as possible habitat loss, fragmentation, or degradation. Water resources, surface water and groundwater are included in the assessment's evaluation of the effects on water quality and quantity. Pollution threats, hydrological changes, and the possibility of flooding or water scarcity are all taken into account. Evaluating the release of gases, dust, and particulate matter into the atmosphere is known as air quality. Both the contribution to more general air pollution issues and the effect on local air quality are assessed. Soil and land use, the EIA looks at how certain land uses and soil quality are affected, such as soil erosion, pollution, and loss of. The public's involvement in the C and EIA processes. A key component of the C and EIA processes is public engagement, which guarantees that stakeholders and the general public's opinions and information are taken into account. This participation helps in a number of important ways, increasing openness and confidence. Participation from the public fosters confidence between the community, authorities, and developers as well as increases transparency in the assessment process. Enhancing assessment quality, public input can contribute extra information and first-hand experience from the area that may not otherwise be available, making evaluations more thorough and accurate. Finding alternatives and concerns, involving the community and stakeholders can help identify potential effects and concerns that were not previously thought of. It might also be useful in locating other strategies. In summary, large-scale residential or commercial project planning and development require the use of EIAs and Cs as essential instruments. By encouraging sustainable development and halting environmental degradation, they make sure that environmental factors are taken into account when making decisions. Developers can improve project sustainability, lessen environmental impacts, and advance the larger objective of environmental conservation by adhering to the standardized procedures of Cs and EIAs. 2024, Zoning Regulations and Land Use Planning. Basics of Land Use and Zoning. Zoning and land use regulations control how real estate is developed and used. Zoning is the most often used type of land use restriction. Zoning laws and limitations are used by municipalities to manage and steer real estate development. Zoning laws have been enacted by practically all significant American cities since New York City's 1916 adoption of the first one. Zoning regulations, what are they? Zoning is used by municipal administrations, such as city councils, to meet their demands. Zoning primarily serves to split a municipality into the following districts, or zones: industrial, commercial, residential. The majority of these zones are distinct from one another, and each district's usage of land is comparatively consistent. There will be more specific limitations within each of these three primary categories of districts. Among them are, certain specifications for the kinds of constructions that are permitted where the utility wires are located, limitations on auxiliary structures, setbacks of buildings from streets, and other borders, building dimensions and height, count of the rooms. These limitations might also apply to frontage of lots, minimum size of a lot, side, back, and front yards, parking away from the street, the quantity of residential units. Certain regions may only be allowed for single-family, multifamily, or townhouse dwellings according to regulations. Preservation of historic or culturally significant features may be mandated by zoning laws. Managing growth. Land use regulation encompasses more than just controlling existing structures and usage. Its primary goal is to guide future growth. The final result of the planning process that most communities employ is a comprehensive or master plan. A comprehensive plan creates an official map for a municipality. It is carried out by ordinances that regulate, zoning laws that control the construction of subdivisions, layouts of streets, plans for public areas, and building regulations. Subdivisions built by future developers must follow the official zoning plan or map. Regional and statewide planning has received more attention in the last few years. Realizing that a municipality's activities will often have a significant impact on nearby cities, sometimes in ways that are paradoxical and in contradiction. These planning projects make it possible to develop a regional plan with a single, all-encompassing vision and set of rules. Restrictions on zoning law. Zoning and land use laws can be contentious since they limit property owners' ability to utilize it how they would like to and can otherwise. It is also difficult to pinpoint exactly what land use regulations governments can and cannot impose. According to court rulings, a zoning ordinance is legal if it is not arbitrary and makes sense. It is reasonably and significantly related to public health, safety, comfort, morality, and welfare in general. The methods used are deemed to be fairly necessary to achieve the goal. Because these elements are subjective, there is a great deal of potential for dispute and, occasionally, lawsuit. In this field of law, one particularly challenging query is how far. Difficulties with zoning laws. There are many more limitations on the government's ability to control how land is used. Any such limitations could serve as a foundation for contesting rules. Zoning regulations have to make sense in light of all relevant circumstances, including the municipality's justifiable requirements, the restrictions objective, the land's location, dimensions, and physical attributes, the neighborhood's personality, their impact on the associated property's value. Zoning is justified by the idea that it advances the general welfare of the community in line with an all-encompassing plan. For instance, it might enhance aesthetics and homeowner safety by establishing minimum quantities for lots, ratios of floor area. Building elevations inside residential areas. Property owners in residential zones who depend on inexpensive housing may also be protected by zoning regulations. Reuters, 2024, Community Engagement in Site Planning. A current local plan, which replaces and consolidates earlier development plan documents, DPDs, including core strategies, development management policies, and area action plans, is required of all local authorities. Additionally, policies outlined in local plans must be evaluated and revised as needed at least once every 5 years. Local plans address all of the needs and possibilities that a community has while outlining a vision and framework for the area's future development over a period of 15 years. Ensuring enough, affordable housing, fostering a strong local economy, and mitigating and adapting to climate change are some of the issues at hand. Even though local planning calls for formal engagement procedures, you should view it as a longer-term process that goes beyond a single point in time if you want to effectively develop ties with the people in your community and earn their trust in your work. You may more effectively allocate resources and determine what kind of supporting infrastructure will be required by consulting your community and learning about their top priorities. Future development initiatives will benefit from increased support as a result, and your council's decisions will receive higher marks in. The best ways to involve your community in local planning consultations, whether it is a new plan or an update to an old one. The first step in any local plan consultation process is to identify important priorities by soliciting community feedback. You will undoubtedly concur that you must involve as many community members as possible in the process. However, it might be challenging to meaningfully assist residents in navigating choices and challenges. People must be engaged and found it easy to participate if you want to get insightful feedback. Thankfully, there are several options for doing this. Give a background. Why are we coming up with this plan? What will it change, and why does it matter? Members of the community will become more interested in getting part if you can help them see how important the decisions being made are. Think visually. When disseminating information, try using infographics, interactive maps, mind maps, or other visual components. To spark engagement, material must be simple to understand and retain. Divide your plan into manageable, more focused sections. If your plan includes a section on building greener spaces, you can further segment this section based on neighborhood-specific topics, green space availability, or current issues. This enables members of the community to concentrate their involvement efforts on the subjects or regions that are most important to them. Philae, 2024, Chapter 4, Building Materials and Technology Overview of Construction Materials. The variety of building materials used in different projects is the foundation of the construction business. A growing array of sophisticated materials designed to increase performance and sustainability have been added to traditional materials like concrete, wood, steel, and brick in recent years. Building materials are commonly classified into two origins, natural and man-made. However, both must be made or treated before they are utilized in construction. The list of materials used in building construction is as follows. Steel, iron and carbon are combined with additional components to form steel, a hard metal that is more durable and damage-resistant than iron. For instance, stainless steel has more chromium, which helps it withstand oxidation and corrosion. Because of its remarkable strength, and in spite of its weight, it is the preferred material for building contemporary structures and sizable industrial complexes. Cement, an essential component of construction. Cement helps other materials adhere to one another by hardening and adhering to them. It's usually combined with gravel and sand rather than utilized by itself. In order to make mortar, which is needed to hold bricks and stones in place during construction, cement and fine sand are frequently combined. It produces concrete when combined with sand and gravel. This adaptable substance is employed in a variety of construction tasks. It is a cornerstone of construction because of its capacity to solidify and bond, guaranteeing that buildings and other structures endure the test of time. Concrete is a unique building material that is created by combining artificial elements with small and large particles of crushed stone, gravel, and recycled concrete. A liquid binder, generally cement, holds these components together while they dry and progressively solidifies. Portland cement, the most widely used kind, is created by heating clay and limestone and then adding gypsum. Portland cement becomes the durable material known as concrete when combined with these particles and water. Many of the powerful structures that surround us are made of this substance. Ready-mix concrete, prepared mixture, pre-mixed and ready for use. Concrete is a practical building material that is made at a plant located off-site and delivered to construction sites. It is a carefully calculated and blended mixture of cement, water, and aggregates like sand and gravel that is made at a concrete plant. On building projects, this ready-to-use combination saves time and effort by ensuring consistency and quality. It is easily poured by contractors into molds or formwork, enabling accurate placement and curing. Admixtures are additional ingredients that are occasionally added to concrete to manage its setting time or to make it easier to handle so that it may be transported to a construction site quickly. Binding wire is essential to construction since it keeps various parts firmly attached. Tying reinforcing bars, or rebars, at connection points is especially helpful in guaranteeing the stability of the building. Mild steel is typically used to make binding wire. Constructional binding wire, straightened cut wire. This wire offers a strong and reliable binding, making it perfect for use in construction. Black annealed binding wire. This wire is perfect for regular tying needs because it's easy to work with and guarantees a tight grasp. Iron binding wire, galvanized. This wire is robust, corrosion resistant, and appropriate for long-term uses. Rebar wire with small coils especially made to hold rebar in place, guaranteeing structural stability. Tie wire loop adaptable and helpful for many different construction-related tying applications. Wire binding for packing, mostly used to secure materials and items during packaging. U-style binding wire. This wire, which resembles the letter U, is designed to meet particular binding specifications. Galvanized wire is perfect for outdoor applications as it offers additional rust prevention. Wire made of stainless steel. It is appropriate for outdoor and maritime applications since it is corrosion resistant. Brass wire, widely utilized in a variety of industries, this wire is renowned for its strength and resistance to corrosion. Aluminum wire, this wire is corrosion resistant and lightweight, making it perfect for some applications where weight is an issue. PVC coated binding wire, because of its resilience to weather, it provides additional protection and is frequently used in tough outdoor locations. Wood. For millennia, wood has been a reliable building material due to its versatility and ability to come from trees. There are many different kinds of stones, and each has special qualities and applications. Because of its strength, resilience, and visual appeal, wood is a highly sought-after building material that can be used for flooring, furniture, construction, and a myriad of other purposes. When it's chopped or pressed into different shapes like timber, boards, and planks, it's employed in building. Because of its regenerative nature, it is also an environmentally sustainable option for architecture and design. When wood is sourced ethically, for example, by earning an FSC, Forest Stewardship Council, certification, it guarantees that forests are maintained responsibly, supporting local communities and encouraging the preservation of biodiversity and natural environments. Stone. Stone is an organic building material that was created by geological processes over many millennia. It comes in a variety of forms, each with distinct colors and textures, such as granite, limestone, marble, and more. Stones are construction materials that provide building strength. They are used for floors, walls, foundations, and decorative features. Stone materials are a popular choice in building because of their strength and resistance to harsh weather, which guarantees both long-lasting function and a rustic look. Bricks. One of the most basic and ancient building materials still in use today is brick. Usually, kiln-fired clay is used to make them. Bricks are frequently used to build structures such as walls, buildings, and other masonry works. They are materials that can be used to construct a home that offers a variety of design options. They are available in many forms, sizes, and colors. Bricks are building materials that have endured over time in the construction business because of their solidity and capacity to insulate. They also provide architectural projects a classic, conventional appearance. Blocks. Blocks are prefabricated building pieces composed of aerated concrete, clay or concrete. These pieces come in a variety of sizes and shapes, each designed to meet unique building requirements. In building projects, they are essential to the construction of walls, partitions, and structural components. Because of their strength, stability, and simplicity of installation, blocks are a popular choice for both residential and commercial constructions. Aggregates. Granular materials used in construction. Aggregates are usually made of recycled materials like concrete and asphalt or crushed stone, gravel, and sand. These elements function as the fundamental building blocks for a variety of construction projects, including the construction of buildings, bridges, and roadways. By provide structural support, aggregates help distribute weight evenly and increase the strength of asphalt and concrete mixtures. Aggregates can be precisely adjusted to fulfill individual construction requirements due to their wide range of sizes and types. Selecting the appropriate building materials for construction becomes crucial while creating a home. Patry, 2021, 4.2 Innovations in Sustainable Materials. Today, nearly every significant business uses metals, cement, batteries, glass, plastics, and more, accounting for 20% of greenhouse gas emissions worldwide. By 2040, the weight of human impact might surpass 3 teratons, double the weight of all living things on Earth, if we continue to use man-made materials at the current rate. The idea that the new, sustainable materials we are developing today must be safe for the environment, decrease waste, and lower carbon emissions is fundamental to solving this challenge. To understand how new materials might affect change, watch this little video. Rather, to integrate and optimize interdisciplinary processes and carry out complex tests like those for material strength, flexibility, heat resistance, and chemical reactivity, a single platform with cutting-edge tools and simulation capabilities is required. Working on a single platform expedites the reduction of time-consuming and costly processes, allows for the agile navigation of complicated rules and policies, and decreases the amount of resources needed for lab testing and physical prototyping. Maximize the virtual twin's use in material innovation. Using scientifically accurate 3D models as a basis, businesses may perform molecular simulations to predict the behavior of various material qualities during the construction, usage, and recycling processes along the entire value chain. By offering a flexible environment for performing virtual experiments, simulating several what-if scenarios, and producing only the most sustainable solution, the virtual twin saves time and money. Build reliable digital prototypes to support material development and repurposing. To develop low-carbon materials and guarantee material compliance, perform subatomic level research and experimentation to stimulate creative thought. Accurately, precisely, and quickly link fundamental physics and chemistry of the materials to practical insights. SYST MES, 2024, Repurposed Resources. Bio-based materials. Repurposed resources. Materials based on bio-eco-friendly insulation. Minimal VOC items. Astute materials. 4.3 Material life cycles and environmental impact. As was previously noted, reusing products can be classified as a challenging way to enhance the material life cycle. This is because returning products to the maker or distributor after reuse necessitates the construction of extra infrastructure. Reusing products can be considered the ultimate form of extended producer responsibility in this regard. Nonetheless, a wide variety of unique product designs can be found in every product category, as producers frequently aim to set themselves apart from rivals. This necessitates a very rigorous system of product separation and return where each particular product can be linked to a certain manufacturer. Practically speaking, this probably isn't possible. Two kinds of systems do appear to be workable. The first system was previously covered. In this case, the product is leased rather than sold, and the producer keeps ownership of it. In this instance, the product's producer has the ability to retrieve it at the end of its useful life and always knows where it is. Large, costly, electronic, copy machines and other professional market equipment are typical products for such a system. This system's significant flaw is how quickly technology is changing various product categories. As a result, parts from recycled products are frequently out of date. Material recycling is the second best choice in these circumstances. But one can wonder if giving the goods back to the owner is a better option for material recycling than using a broad collecting system. The latter is much easier to organize and can benefit from scale issues. The second system is an effective returning system that makes use of the standardization principle. In this instance, a number of distributors and producers agree on a standardized product that is produced by these entities. Examples are the returnable soda and beer bottles found in several European nations. They are of the same size, made of the same material, and have the same design. The labels are only different. All bottles can be spread between all producers thanks to this technique. This makes the returning system's configuration simpler, but it limits the ability of individual manufacturers to create new, competitive product designs and necessitates the cooperation of all significant producers and distributors. The challenge in creating this kind of return system is that it calls for a lot of businesses, manufacturers, distributors, and retailers, and all parties must agree on the system's specifics. And extensive management is required to maintain the system. Transaction costs result from this, which businesses want to minimize. Heckert, 2004, Smart Building Technologies. The way buildings function and engage with their occupants and the surrounding environment is changing as a result of the incorporation of smart technologies into building design and construction. Utilizing sensors, automation, and communication networks, smart building solutions improve productivity, security, and user experience. Smart buildings are those that use technology to maximize occupant comfort, efficiency, and resource use. These structures are outfitted with a wide range of cutting-edge technology, including the Internet of Things, IoT, augmented reality, AR, and artificial intelligence, AI. Comfort, productivity, and energy efficiency are just a few of the criteria that smart buildings are made to track. They have digital sensors installed to do this, which may collect data and communicate with software to offer improvement chances. For example, digital sensors can detect which days and times a business most regularly uses a meeting room or other portion of the office that is rarely used. Then, it can modify energy use such that, when this space is most likely to be used, heating and lighting are automatically turned on. In a parking lot, lighting and temperature can also be changed according to usage, which helps save energy. Figure 3. Smart buildings. Smart building systems are becoming more and more ubiquitous in many of the largest cities in the world. They are not just a futuristic pipe dream. Here's only one instance: Fraser's Tower, located in Singapore. Microsoft, a big player in the IT industry, is housed in Singapore's 38-story office tower, Fraser's Tower. Utilizing a smart building system coupled with Microsoft apps such as Office 365 and Outlook, this tower exemplifies a connected building, enabling optimal performance for both the building and its residents. Fraser's Tower also uses smart sensors to keep an eye on lighting, temperature, and air quality. Furthermore, Fraser's Tower is paving the way for further structures of a similar type by utilizing a digital twin, which is a virtual reproduction of the actual skyscraper. To achieve net zero by 2050, the built environment must address all aspects of the building life cycle, from the carbon emissions produced during construction to the energy consumed after a facility is put into use. In addition to implementing cutting-edge construction methods and restoring older structures rather than demolishing them, our industry must promote smart technology and the substantial advantages it offers for sustainability as well as the well-being of the people who live there on a daily basis. Anonymous, 2024, Chapter 5, Energy Efficiency in Buildings. Building energy efficiency is essential to the global efforts to minimize energy costs, reduce greenhouse gas emissions, and promote sustainability. This chapter explores the many facets of energy efficiency, including patterns of consumption, design approaches, integration of renewable energy sources, and management systems. 5.1 Energy consumption in the building sector. Among the biggest energy users, buildings contribute significantly to both overall energy consumption and associated carbon emissions. Buildings, which include both residential and commercial buildings, account for a significant portion of the world's overall energy use in many nations. Approximately 54% of all delivered energy worldwide is consumed by the industrial sector, which utilizes more delivered energy to 94 than any other end-use industry. 3 different industry kinds can be used to classify the industrial sector: manufacturing that requires a lot of energy, manufacturing that doesn't require a lot of energy, and non-manufacturing. Depending on the type and intensity of economic activity as well as the state of technology, different areas and nations use different fuel mixes and intensities in the industrial sector. The industrial sector uses energy for many different things, including process and assembly, steam and cogeneration, process heating and cooling, and building lighting, heating, and air conditioning. Basic chemicals feedstocks are another category of energy consumed in the industrial sector. Agricultural chemicals are made from feedstocks that are natural gas. In addition to their many other applications, natural gas liquids, NGL, and petroleum products, such naphtha, are utilized in the production of organic compounds and polymers. Data on all industry links that comprise economic activity is provided by gross output, which includes intermediate inputs needed in industrial processes, such as energy, materials, and acquired services. Anonymous, 2016, 5.2 Passive and Active Design Strategies. Efficiency in energy use. Architects and builders can use both passive and active design solutions to improve energy efficiency. These tactics seek to lessen the need for mechanical systems overall and to use less energy. Passive design techniques can drastically lower a building's energy usage because they rely on natural sources for lighting, ventilation, heating, and air conditioning, whereas active design relies on mechanical operations. Lower energy costs and a smaller carbon impact may result from this. Cozy interior. Passive design strategies can provide a comfortable indoor atmosphere by optimizing natural ventilation and minimizing direct light exposure. This can lead to a more comfortable and healthful indoor environment free from drafts, hot spots, and indoor air pollution. Health and well-being. By encouraging natural ventilation, lowering indoor air pollution, and allowing access to natural light, passive design techniques can enhance health and well-being. Strength and lifespan. The use of basic, low-maintenance systems and long-lasting materials in passive design strategies can extend the life of a structure and lessen the need for regular replacements or repairs. Cost-effectiveness. Passive design techniques can minimize the original cost of construction as well as ongoing operating costs by lowering the reliance on mechanical systems, which opens up the possibility of developing sustainable buildings at a cheaper cost to a wider variety of individuals. Durability. By minimizing the building's environmental impact and using less non-renewable resources, passive design strategies are in line with sustainability principles. Important passive design techniques every architect should know. By quickly adopting passive design techniques, AEC professionals hope to produce more environmentally friendly and energy-efficient structures. The main passive design techniques that support the creation of sustainable architectural structures are listed below. Orientation. Orientation is a passive design concept that refers to how a structure is positioned on its site in relation to the wind and sun. Passive solar architecture, which minimizes direct solar exposure and maximizes natural ventilation to reduce energy use and improve indoor comfort, heavily relies on building orientation. It is feasible to lower the requirement for heating and cooling systems and increase indoor comfort by positioning the building to receive the most solar exposure in the winter and the least in the summer. Similarly, it is feasible to produce a suitable indoor climate without using mechanical ventilation systems by orienting the building to take advantage of prevailing winds. Warmth. Improving a building's thermal envelope through insulation can minimize heat gain in the summer and loss in the winter. Insulation is a passive design method. This lowers the amount of energy needed for heating and cooling while also maintaining a comfortable interior atmosphere. To lessen heat transfer, insulation can be added to a building's floor, walls, roof, and windows. The three most popular kinds of insulation materials are foam, cellulose, and fiberglass. The local temperature, the kind of building, and the required level of energy efficiency will all affect the kind and thickness of insulation that is needed. Windows. By allowing natural light to enter a structure, windows help to minimize the demand for artificial lighting during the day. In addition, they offer vistas of the outside world and a link to the surrounding environment, along with ventilation options. By permitting passive solar heating and cooling, windows can also improve a building's thermal performance when they are constructed properly. When constructing windows for passive performance, there are a number of things to take into account, such as frame material, glazing type, orientation, size, and shading. In order to enhance passive solar heating in the winter, windows should be placed on the building's sunniest sides. In the summer, shading devices can be employed to reduce overheating. The thermal efficiency of windows can be enhanced and heat gain or loss reduced by using high-performance glazing and frame materials. Natural air exchange. In addition to lowering interior pollution and enhancing general comfort, proper ventilation also helps to control indoor air quality. By facilitating the passage of air between the inside and outside, it can also contribute to passive heating and cooling. Utilizing windows and other openings to let the flow of indoor and outdoor air is known as natural ventilation. The orientation and size of openings, the usage of shading devices, and the building envelope's overall thermal efficiency are all crucial factors to take into account when designing ventilation systems. Verdant walls and roofs. The concept of green architecture includes the idea of green walls and roofs, which have several advantages such as better air quality, reduced stormwater runoff, enhanced biodiversity, and enhanced insulation and thermal performance. Typically, a building's roof structure is covered in a layer of growing medium and flora that is called a green roof. They can be as basic as simple roof decks covered in vegetation or as sophisticated as large green roofs with multiple soil layers, plant species, and drainage systems. Similar to green roofs, green walls, also referred to as vertical gardens, are made to blend into the facade of buildings. These features can be planted with a variety of vegetation to fit the particular requirements of the building and its location. They can also be created in a variety of ways, such as modular systems and freestanding elements. Buildings and architectural designs that are sustainable now require more and more of these techniques. It's crucial to take into account elements like the kind and quantity of vegetation, the growing media, and the irrigation and drainage systems when planning green walls and roofs. Ensuring the long-term efficacy and sustainability of these features requires proper design and upkeep. Architecture using passive design techniques for different climates. Depending on the climate where their building will be located, architects can employ the basic passive design principles listed below. Strategies for passive design in hot and humid climates. Instead of being positioned on the east and west sides of the structure, the majority of the windows ought to be on the north and south faces. In hot and muggy conditions, cross-ventilation, which involves placing windows on opposing sides of the structure, can be very beneficial. A flat roof can absorb more heat than a sloping roof with overhangs, which can aid to limit heat input. The north and south faces of the building should have windows, not the east and west, according to passive design strategies for tropical climates. The building can be shaded by adding overhangs, fins, or louvres to prevent direct sunlight from entering. A flat roof can absorb more heat than a sloping roof with overhangs, which can aid to limit heat input. Techniques for passive design in cold climates. Warm air can be kept out of the building and cold air kept in with the use of air sealing. In colder climates, double or triple glazed windows are commonly utilized to enhance thermal efficiency. High-quality insulation should be used on the walls, floors, and roofs, utilizing materials like foam, cellulose, or fiberglass. Buildings with moderate climates should be created with passive design strategies to optimize solar radiation, especially on south-facing surfaces during the winter and in shaded areas during the summer. Windows ought to be built to minimize heat gain in the summer and maximize sunlight gain in the winter. The building can be shaded by adding overhangs, fins, or louvres to prevent direct sunlight from entering. Techniques for passive design in hot and dry climates. Structures should be planned to minimize heat gain in the summer and maximize solar radiation in the winter, especially on the south-facing side. Concrete, stone, and tile are examples of materials with light colors that can reflect more heat than materials with dark colors. Cooling techniques for the interior of the building include evaporative coolers and water features. The quality of a constructed environment is enhanced by passive design techniques in architecture, which enhances livability and user experience. In order to comprehend a project's environmental impact, current AEC professionals can employ computational tools like parametric modeling, generative design software, and other building performance analysis software. With the help of these resources, you may produce designs that are more durable, sustainable, and energy efficient. Sharma, 2023, Renewable Energy Integration Perspectives on Renewable Energy by Incorporating Building Integrated Photovoltaics, BIPV. Structures can be turned into active solar generators, improving commercial buildings' ability to produce energy as well as their visual appeal. With the advancement of solar thermal systems, STS, buildings may now be more sustainably constructed and rely less on conventional energy sources for heating, cooling, and hot water. Including renewable energy into business architecture is not merely a fad, rather, it is a crucial change that will improve efficiency and sustainability in the context of commercial buildings. Renewable energy sources like solar, wind, and biomass must be integrated into commercial buildings as our needs for energy grow and environmental concerns intensify. This strategy improves the energy resilience and financial performance of commercial properties while simultaneously reducing the environmental impact of energy usage. Commercial building designs can make a substantial contribution to a future that is more sustainable and energy efficient by adhering to these guidelines. Principles of energy efficiency in the integration of renewable energy. Reducing energy use and maximizing the use of renewable energy sources are the cornerstones of energy efficiency. Energy efficiency, as it relates to renewable integration, is the capacity to capture, store, and use energy produced by renewable sources to meet the energy requirements of commercial buildings with the least amount of waste and environmental damage possible. The importance of data architecture and modular information technology, IT, in improving energy efficiency has been highlighted by recent developments. Commercial buildings can gain from a system where different renewable energy sources and technologies are smoothly integrated, enabling flexible and scalable energy solutions, by implementing a modular approach. With the help of this architecture, energy data can be managed effectively, allowing for accurate tracking, evaluation, and optimization of energy consumption. Energy managers, for instance, may better anticipate demand, integrate different renewable energy sources, and react to variations in the supply and demand of energy with modular IT systems. Anonymous, 2024, Building Energy Management Systems, BEMS, Building Energy Management Systems, BEMS, are essential for improving the sustainability and efficiency of building energy use. In order to monitor, regulate, and optimize the energy consumption of different systems within a building, such as lighting, HVAC, and other electrical loads, a building energy management system, BEMS, usually combines hardware and software components. A closer look into BEMS's elements, advantages, and uses is provided. In order to monitor energy usage and waste, building energy management systems, BEMS, link the lighting, fire, HVAC, and plant room equipment systems of a commercial building onto a single software platform. Building owners, operators, and occupants may optimize energy use and cut expenses across various buildings by utilizing BEMS technology, which can enhance energy efficiency by anywhere between 10 and 30%. It's crucial to remember that building energy management systems, BEMS, are made up of both hardware and software components. To significantly reduce energy use, the majority of BEMS systems rely on hardware such as building management systems, controls, and meters. Systems for managing building energy primarily serve two purposes: provide comprehensive analytics for energy management that identify energy wastage. Establish a procedure for fixing found flaws and mechanical inefficiencies. You can see how a building energy management system uses information from suppliers on the left to enable the results on the right in the graphic below. A building analytics system, such as CIM's Peak platform, receives data from the building's utility, water, and building management systems on the left side. The building analytics system then makes it possible to achieve a number of goals, such as assessing the assets, the building's performance, lowering energy and downtime, and enhancing indoor environment temperatures and circulation. Figure 4: Building energy management systems. As was previously noted, hardware connections and endpoints that pull in operational data are necessary for a building energy management system to function effectively. A building without any sensors collecting data or without a centrally managed building management system, BMS, will have a restricted amount of data that a BEMS system can work with. It is helpful to first comprehend the connecting point of a building energy management system in order to comprehend how it operates, The mechanism for managing buildings. The purpose of the Building Management System, BMS, is control. It does this by centralizing the supervision of all the systems in a building, such as fire safety and lifts. All of the sensors that keep an eye on operational operations, the controllers that compile the data from those sensors, and the human interface that enables simple and rapid control instructions from a desktop or touchpoints make up building management systems. The majority of BMS systems use physical connections, including twisted pair wires, to link controllers and sensors. The most logical location for a building energy management system to access data about a building is through a BMS controller connected to an RJ25 cable, since the BMS wiring is integrated into the structure of the building. You can see how a CIM card is used to connect to a controller and access a building's network in the diagram below. The data from the HVAC, vital utilities, lighting, process equipment, and M systems may now be viewed by the Building Analytics platform. Figure 5. CIM connecting to a building's network using BEMS to improve BMS. Although a BMS is quite good at managing building settings, it is not very good at auditing or energy management. Building management is made more comprehensive by combining a BMS and a BEMS. By combining the sophisticated energy monitoring, optimization, and fault detection capabilities of a BEMS with the conventional control functions of a BMS, this integration improves energy efficiency and system health. This is an illustration of a BEMS. A CIM baser is visible in the center. After establishing a connection with the BMS, this device uses a raw meter, submeter, and other tools to generate root cause alerts, designate actions, exchange images, and document progress. Figure 6. BMS generate alerts, designate actions, exchange images, and document progress. Principal advantages of putting in place a building energy management system. There are several advantages to installing a building energy management system, BEMS. HVAC systems in particular stand to gain since they account for 40% of energy use, and experts estimate that of HVAC energy use is lost owing to failure, deterioration in performance, or misdone controls. The main benefits of utilizing a BEMS system are listed below. Energy efficiency and cost savings, with HVAC systems accounting for around 40% of building energy use. A building energy management system, BEMS, is crucial for optimizing resource utilization and cutting energy use. BEMS provide quick operational adjustments based on real-time energy monitoring, thereby reducing operational expenses and energy waste. Consistently maintaining energy efficiency is made possible by this proactive management. Improved structure efficiency. A building energy management system, BEMS, increases comfort and productivity within a building by maintaining ideal environmental conditions. In order to provide consistent performance, the system dynamically modifies settings based on occupancy and usage in real time. Additionally, a BEMS's predictive maintenance features foresee any problems before they arise, minimizing the need for expensive repairs and equipment downtime. Fault detection and diagnosis, FDD. By employing sophisticated analytics to precisely identify and address problems, a BEMS provides better fault detection and diagnosis than conventional manual inspections. The maintenance process is streamlined and less manual troubleshooting is required thanks to the integration of artificial intelligence, which offers accurate, practical solutions. Environmental impact. By lowering carbon emissions, effective energy management with a BEMS contributes to more general sustainability objectives. By improving environmental compliance and sustainability reporting, a BEMS can assist buildings in obtaining green certifications like LEED, WELL, and BREEAM. This is advantageous for regulatory compliance and stakeholder communication. Rules and regulations adherence. BEMS makes ensuring that energy conservation rules and regulations are followed. They provide the documentation of energy use and efficiency measures for minimum standards like MES, as well as compliance and reporting frameworks like TCFD, SASB, and CDP. Building owners and operators can improve operational effectiveness, sustainability, and compliance in addition to energy conservation by using a BEMS. The system's value in contemporary, Proactive building management is further highlighted by the added benefit of accurate issue identification and diagnosis. A BEM system can also be used for energy benchmarking, showing how a building's energy performance stacks up against other comparable buildings. Building energy management systems, a synopsis of their history. The modern forms of building energy management systems are relatively recent. The commercial buildings with the lowest emissions typically use heat pumps, BEMS, and other cutting-edge technologies to reduce their emissions. The least energy-intensive structures in the U.S. currently use 82% electricity and 38% less energy per square foot. Let's take a look back at BEM's past to see how they changed the commercial real estate sector. Integration and centralization. As commercial buildings became increasingly complex in the 1980s and 1990s, there was an increasing demand for integrated solutions. Building management systems, BMS, which combined several subsystems including lighting, HVAC, and security into a single centralized interface, came into being during this era. The first steps towards the complex BEMS of today were defined by this integration. Digitalization and the dawn of data. In the late 1990s and early 2000s, the building management sector saw a digital revolution. The proliferation of sensors and the Internet's development made it possible for EMS to collect real-time data, which led to increased productivity, precise monitoring, and the introduction of predictive maintenance capabilities. Green movement and sustainability. The 2000s global movement towards sustainability led to a reinterpretation of EMS's original mission. In addition to lowering costs, EMS started to be a crucial component in lowering the carbon footprints of buildings, supporting LEED and other green building certifications. IoT and smart buildings. In the 2010s, BEMS reached new heights with the integration of the Internet of Things, IoT. With linked devices interacting seamlessly to provide more precise control, automation, and energy optimization based on real-time data, the era of smart commercial buildings has come. Predictive analysis and artificial intelligence. The most sophisticated BEMS available today make use of machine learning and artificial intelligence, AI. By using historical data, weather patterns, and occupancy trends, these systems can foresee future energy demands in addition to meeting immediate needs. This predictive analysis capability makes these systems highly effective. This is an example of a proactive approach to energy management with the goal of reducing waste and increasing effectiveness. Building energy management systems. Future building energy management systems, BEMS, are a quickly changing field, with a number of new developments and trends influencing its direction. Integration of renewable energy sources. In order to provide a more sustainable energy mix, future BEMS are anticipated to integrate with renewable energy sources like solar and wind power more and more. Advanced data analytics. Using increasingly advanced sensors and integrating the Internet of Things, enhanced data analytics will offer deeper insights into energy consumption, efficiency, and possible savings. Predictive maintenance. By spotting possible system breakdowns before they happen, AI and machine learning algorithms will improve predictive maintenance capabilities. Tenant preference. It is anticipated that building occupants will start to anticipate a reduction in their energy and carbon footprint. Reducing energy consumption is cited by 84% of respondents in a recent CBRE poll as having an influence on real estate decisions. In conclusion, AI-driven, advanced systems that optimize energy use and improve building operations have replaced manual, basic methods in the field of building energy management. Energy economy, financial savings, improved building performance, and regulatory compliance are some of the main advantages. BEMS will play an ever more crucial role in managing building energy sustainably and effectively as technology develops. We advise facility managers and building operators to think about enhancing or introducing a BEMS. By doing this, you not only set up your facilities for future technological developments but also get immediate operating benefits. Holbert, 2024, Chapter 6, Indoor Environmental Quality. The term indoor environmental quality, IEQ, describes how well a building's interior environment meets the needs of its occupants, especially with regard to their comfort and well-being. The essential elements of indoor environmental quality, IEQ, that are covered in this chapter include thermal comfort, lighting design, acoustic considerations, and the incorporation of biophilic design to enhance well-being. Importance of indoor air quality. In order to guarantee a healthy living and working environment, indoor air quality, or IAQ, is essential. Many health concerns, such as allergies, chronic diseases, and respiratory disorders, can be brought on by low IAQ. Among the variables affecting IAQ are indoor air quality control and improvement trends, associated human diseases, and indoor air pollution. Millions of people die each year as a result of indoor air pollution, IAP, which poses a major risk to human health. Numerous contaminants have the potential to cause indoor air pollution, IAP, thus it's critical to pinpoint their primary sources and concentrations as well as develop control and improvement plans for IAQ. The main sources of major pollutant emissions, their health impacts, and concerns about IL-based disorders, such as sick building syndrome, SBS, and building-related illness, BRI, are reviewed and evaluated critically here. Furthermore, the methods and techniques for regulating and lowering the concentrations of pollutants are highlighted, and the latest developments in the endeavors to address and enhance IAQ, along with their corresponding benefits and possibilities, are outlined. Future IAQ control and improvement are expected to benefit from the development of innovative materials for sensors, IAQ monitoring systems, and smart houses. The circumstances of the indoor environment have a significant impact on human welfare because most individuals spend 90% of their time indoors, mostly at home or at work. The World Health Organization, WHO, estimates that 3.8 million fatalities per year are caused by indoor air pollution, or IAP. IAP can be produced by residents' activities inside of houses or buildings, including cooking, smoking, using electronics, using consumer goods, and emitting emissions from building materials. Particulate matter, PM, aerosol, volatile organic compounds, VOX, carbon monoxide, CO, biological contaminants, and others are among the harmful pollutants found inside buildings. As a result, studies on air quality regulation have started to focus more on indoor settings over the past 10 years, reflecting changes in lifestyle that are associated with higher levels of urbanization. It has been shown that lower IAQ can have a detrimental impact on human health by leading to illnesses connected to buildings. Numerous disorders can arise from exposure to IAP, both in the short and long term. As a result, creating monitoring systems is essential to controlling IAQ. IAP typically consists of a complicated mixture of several gaseous components and particulate matter. IAP compositions vary greatly based on ventilation conditions, emission rates, and sources. Therefore, identifying the sources of air pollution is essential for efficient IAQ treatment. Furthermore, it is seen to be crucial to establish monitoring systems for determining the concentrations of indoor pollutants as well as important management and improvement measures for IAQ. In this paper, we give a thorough overview of the main sources of indoor air pollution, IAP, and IAQ control strategies. We also highlight the sources, traits, and health effects of each IAP, identify and discuss health problems and illnesses linked to buildings that are associated with a decrease in IAQ, and finally, present the most recent and popular strategies for controlling and reducing pollutant concentrations and improving IAQ. It is anticipated that innovative materials-based sensors, smart monitoring systems, and smart houses will be among the promising approaches for IAQ control and monitoring in the future. The terms indoor air pollution, IAP, and indoor air quality, IAQ. IAQ is defined by the EPA as the air quality inside and around buildings and structures, with a focus on how it affects building occupants' comfort and health. In contrast, indoor air pollution, or IAP, refers to the presence of pollutants in high concentrations in non-industrial buildings' indoor air. These pollutants include particulate matter, PM, volatile organic compounds, VOX, inorganic compounds, physical chemicals, and biological factors. All of these pollutants have the potential to be harmful to human health. IAQ has grown as an area of study and has emerged to protect people from such contaminants. Pollutant concentrations, thermal conditions, temperature, airflow, relative humidity, light, and noise are the primary factors used to evaluate indoor air quality, IAQ. IAQ's thermal conditions are important for two main reasons. Relative humidity and temperature adjustments can easily address a number of issues related to low IAQ. And building materials in high-temperature buildings can be greatly liberated. Three main components have been found to have a substantial impact on indoor and outdoor quality, IAQ, in residential areas and structures, I. Outdoor air quality, 2. Human activities within buildings, and 3. Building and construction materials, equipment, and furnishings. Because pollutants can move from outside to inside buildings, it is well recognized that building airtightness and external contaminant concentrations have a significant impact on indoor air quality, IAQ. Through ventilation, contaminants from outside the building are brought into when their concentrations rise. As a result, in addition to the lifetimes and mixing ratios of these contaminants, the ventilation rate has a significant influence on the link between outdoor air pollution and IAQ. IAP is typically caused by waste gases, tobacco smoke, pesticides, solvents, cleaning supplies, particles, dust, mold, fibers, and allergies released during daily operations. Additionally, millions of mold, fungi, pollen, spores, bacteria, viruses, and insects like roaches and dust mites thrive because of the favorable conditions that humans generate. Particulate matter, PM, carbon dioxide, CO2, sulfur dioxide, SO2, carbon monoxide, CO, and nitrogen dioxide, NO2, are among the gases released into indoor air environments by combustion sources and cooking actions. Furthermore, devices like printers, photocopiers, computers, and other office equipment release volatile chemicals and ozone, O3, into the air. Common construction materials can release harmful substances, i.e., alkanes, aromatic compounds, 2-ethylhexanol, acetophenone, alkylated aromatic compounds, styrene, toluene, glycols, glycolesters, texanol, ketones, esters, siloxane, and formaldehyde. Examples of these materials include poly, vinyl chloride, PVC floor covering, parquet, linoleum, rubber carpet, adhesive, lacquer, paint, sealant, and particle board. Crucially, ventilation system operation and design also have a big impact on indoor air quality. Ventilation produces appropriate IAQ and a healthy interior environment by replacing the stale indoor air with fresh outdoor air. There are numerous advantages to having a building's ventilation system operating, including, I. Supplying fresh air and oxygen for human respiration, 2. Diluting indoor air pollutants to short-term exposure limits of dangerous substances as well as smells and vapors, 3. Controlling indoor humidity, 4. Using outdoor air with low aerosol concentration to control aerosols inside buildings, and b. Establishing appropriate air distribution and fostering a comfortable and healthy atmosphere. Including, I. Mechanical ventilation systems, which circulate air between interior and outdoor spaces mechanically through the use of fans or blowers, and 2. Natural ventilation systems, which perform the same thing without the need for mechanical devices. In some buildings or climates, natural ventilation systems are inadequate, even though the residents may readily embrace them. The widespread usage of mechanical ventilation systems in buildings these days dramatically raises energy consumption. In order to reduce energy consumption and promote the use of sustainable technologies, hybrid ventilation systems are made to benefit from both mechanical and natural ventilation systems. The drawbacks of natural ventilation will be made up for in hybrid ventilation systems by mechanical components. In summary, ventilation is crucial to achieving appropriate indoor air quality, IAQ, in building HVAC systems, but it also contributes to energy consumption. Therefore, Optimizing building ventilation systems is essential for raising energy efficiency as well as increasing occupant IAQ and reducing the likelihood of health issues as a result. Leach J.A., 2022, Primary Pollutants in Indoor Air Quality. It has been established that a wide range of indoor air contaminants negatively affect both human health and IAQ. NOx, volatile and semi-volatile organic compounds, VOx, SO2, O3, CO, PM, radon, hazardous metals, and microbes are the principal indoor air pollutants. Table 1 lists several prevalent contaminants along with their origins and health consequences. While some of them are native to the outdoors, others can be found in both indoor and outdoor settings. Generally speaking, there are 4 categories of indoor air pollutants: organic, inorganic, biological, and radioactive. Table 1 Common indoor pollutants and their effects on human health. Specific matters. PM is described as carbonaceous particles combined with reactive metals and organic compounds that have been adsorbed. Sulfates, nitrates, endotoxin, polycyclic aromatic hydrocarbons, and heavy metals, iron, nickel, copper, zinc, and vanadium, are the principal constituents of PM. PM is typically categorized as follows: I. Coarse particles, or PM10 with a diameter less than 10 m, 2. Small particles, or PM2.5 with a diameter less than 2.5 m, and 3. Ultrafine particles, or PM0.1 with a diameter less than 0.1 m. Since PM can occasionally be inhaled and harm the heart and lungs, as well as have major negative health impacts, it is very alarming. It has been demonstrated that indoor PM levels frequently surpass outside levels. The main sources of PM in buildings include cooking, smoking, using machinery, burning fossil fuels, and engaging in recreational activities at home. The health risks associated with PM 0.1, which is produced when fossil fuels burn, are higher than those associated with PM10 and PM 2.5 because it can enter small airways and alveoli. Cooking and cigarette smoking are the main contributors of indoor air pollution, while cleaning tasks typically contribute less to indoor PM, according to studies on the concentration of key indoor pollutants. One of the main causes of indoor PM 2.5 is smoking, with estimates of increases in households including smokers ranging from 25 to 45 g/m3, and a higher concentration in the winter than in the summer. Research on cooking activities has demonstrated that the burning of food, wood, and oil releases millions of particles, 106 particles/cm3, the majority of which are ultrafine particles. Furthermore, these tiny particles have the potential to migrate throughout the building, not just to the kitchen but also to the living room and other rooms, endangering the health of the occupants. In the meantime, 25% of the interior PM concentrations are likely to be caused by other common human activities including moving about and sitting on furniture. In conclusion, the source strengths for human activities were determined to be between 0.1 and 1.4 mg-min1 for PM10 and between 0.03 and 0.5 mg-min1 for PM2.5. COVs. Volatile organic compounds, VOx, are defined as gases that are released from liquids or solids and contain a range of different chemicals. One of the most common VOx is formaldehyde, a colorless gas with an unpleasant odor that is emitted from a variety of building supplies, including glues, plywood, and particle board. Regardless of the location of the structure, interior surroundings have VOC concentrations that are at least 10 times higher than outdoor ones. In general, there are 4 main sources of indoor volatile organic compounds, VOX, I. Human activity, such as cooking, smoking, and using cleaning and personal care products. 2. Indoor chemical reactions. 3. Penetration of outdoor air through ventilation systems and infiltration. And 4. Building materials. Air exchange rates, home size and age, building improvements, outside VOC levels, and door and window openings can all have an impact on the quantity of volatile organic compounds, VOCs. Furthermore, it has been shown that during 90-minute cooking times, roughly 50 distinct VOCs are detected. The WHO divided volatile organic compounds, VOCs, into 4 categories because they are organic compounds with low boiling points, TB, that readily volatilize even at room temperature. First, there are the very volatile organic compounds, VVOCs, with TB, 50 to 100 C, then there are the volatile organic compounds, VOCs, with 100 C TB 240 C, then there are the semi-volatile inorganic compounds, SVOCs, with 240 C TB 380 C, finally, there are the particulate organic matter, POM, with TB 380 C. 3 main routes typically lead to exposure to volatile organic compounds, VOCs, emitted from consumer products, ingestion, skin contact, or inhalation. Short-term exposure to low concentrations of volatile organic compounds, VOCs, does not usually have a significant negative impact on most individuals, but long-term exposure to certain VOCs is thought to pose significant health hazards, including the possibility of cancer. In terms of SVOCs, transdermal absorption straight from the air contributes more than inhalation intake does. NOx. The 2 main nitrogen oxides are nitrogen dioxide, NO2, and nitric oxide, NO, and they are both connected to combustion sources like heaters and cooking stoves. NO and NO2 ambient concentrations fluctuate greatly based on local sources and sinks. When gas stoves and heaters are used, interior levels frequently surpass outdoor levels. However, their typical concentration in buildings without combustion activities is half that of outdoor levels. Since NO2 is quickly formed from NO under ambient conditions, NO2 is typically regarded as a major pollutant. Nitrous acid, HNO, a potent oxidant and frequent indoor air contaminant, is created when NO2 and water mix. It has been shown that indoor NO2 levels depend on both interior and outdoor sources. As a result, high outdoor NO2 levels from combustion or nearby traffic sources can affect indoor levels. It was noted that indoor NO2 levels are significantly impacted by the separation between buildings and roads. Furthermore, NO2 levels in buildings are influenced by the air exchange between indoor and outdoor spaces. 49. Smoking and appliances that burn wood, gas, oil, coal, or kerosene such as stoves, ovens, water heaters and fireplaces are also significant indoor sources. Ozone. The primary photochemical interactions of O2, NOx, and VOCs in the atmosphere form ozone, a potent oxidizing agent. Unfortunately, because of its delayed reaction with most airborne pollutants, it cannot be employed to remove other indoor chemical pollutants. Ozone makes it possible for a number of indoor contaminants to react quickly, but the byproducts of this reaction can irritate people and harm materials. Indoor ozone is mostly produced by electrical device activity and the outside environment. Devices used in offices such as photocopiers, air purifiers, and disinfectants frequently release ozone gas indoors. These devices fall into 2 categories for their ozone emission mechanisms: photochemical and corona discharge. It has been demonstrated that a number of things affect indoor ozone levels: the ozone level outside, interior emission rates, air exchange rates, surface removal rates, and interactions between other chemicals and ozone in the air are the first 5 factors to consider. The air exchange rate determines the general range of indoor ozone levels, which is 20% to 80% of outside ozone levels. Although skin contact is another known vector, breathing is the main way that humans are exposed to ozone. Of the sulfur oxides, SOx, that are found in the atmosphere, sulfur dioxide, SO2, is the most prevalent gas. Fossil fuel burning is the main source of SO2, which joins forces with PMS and aerosols to create a complex mixture of unique air particles. Ventilated gas appliances, oil furnaces, kerosene heaters, wood or coal stoves and tobacco smoke are examples of indoor sources of SO2 emissions. Furthermore, it is believed that one of the primary sources of indoor SO2 is outside air. SO2 concentrations inside are frequently lower than those outside. Because SO2 is rapidly absorbed by interior surfaces upon reactivation, indoor emissions are often negligible. Buildings are reported to have hourly SO2 concentrations of less than 20 parts per billion. Humans are only exposed to SO2 by inhalation, which can impede respiratory function. Cox combustion processes including cooking and heating are the principal sources of carbon monoxide, CO, in indoor air. Moreover, CO can infiltrate indoor spaces through outside air permeability. Unvented kerosene and gas space heaters, leaking chimneys and furnaces, backdrafting from wood stoves, gas water heaters, fireplaces and furnaces, gas stoves, generators and other gasoline-powered equipment and tobacco smoke are some of the major sources of indoor CO emissions. When there are no gas stoves in a building, the typical CO concentration is between 0.5 and 5 ppm, but when there are gas stoves nearby, the concentration can go up to 30 ppm. Exposure to CO can have detrimental consequences on health, including I. effects on cardiovascular and neurobehavioral systems at low concentrations, and 2. unconsciousness or death at high concentrations. The colorless and odorless gas carbon dioxide, CO2, is a well-known component of the Earth's atmosphere and a significant human metabolite. Fossil fuel burning is the main cause of the ambient air's average 400 parts per million CO2 content. The indoor CO2 level has recently been used as a benchmark for ventilation management and IAQ assessment. The OSHRI standard states that in order to protect human health, indoor CO2 concentrations should be kept below 700 ppm. Exposure to CO2 concentrations of 3000 ppm has been shown to exacerbate headache intensity, weariness, drowsiness, and difficulties focusing. Hazardous metals, either natural processes or human activity, releases heavy metals into the atmosphere. IAP by heavy metals can be caused by a number of things, such as smoking, fuel-consuming items, construction materials, and the infiltration of environmental pollutants, such as dust and soil. When ingested, absorbed via the skin, or inhaled, heavy metals found in indoor dust can have a negative impact on one's health. Based on their effects on people, heavy metals in indoor air are divided into two main groups, according to the International Agency for Research on Cancer, IARC: cobalt, CO, aluminium, Al, copper, Cu, nickel, Ni, iron, Fe, and zinc, Zn, are examples of non-carcinogenic elements. 2. Carcinogenic and non-carcinogenic elements include arsenic, as, chromium, Cr, cadmium, Cd, and lead, Pb. As, Cr, Cd, and Pb are typical heavy metals that are known to cause malignancies. In addition, Cd and Pb, along with a few other heavy metals, can induce carcinogenic effects such as poor growth development, harm to the neurological system, and cardiovascular disease. According to reports, the greatest concentrations of As, Al, Cr, Cd, Co, Cu, Ni, Fe, and Zn in indoor air are approximately 486.80, 7100, and 50.00, 254.00, 8.48, 43.40, 513.00, 471.00, 4801.00, and 2293.56 G/G, respectively. Pb levels have been found to vary between 5.80 and 639.10 G/G. Aerosols. Indoor gas-to-particle reactions produce secondary aerosols, which are either the result of indoor gas-to-particle reactions or primary aerosols from various indoor sources. Moreover, indoor aerosols are probably produced by outside particles that find their way inside. While secondary organic aerosols, SOAs, are created during the gas-to-particle conversion process of volatile organic compounds, VOX. Secondary inorganic aerosols are PMS made up of inorganic elements, such as those from anthropogenic or crustal sources and water-soluble ions. Moreover, one of the most well-known species in PM2.5 is carbonaceous aerosol, which includes SOAs and elemental carbons generated during incomplete combustion. A subgroup of atmospheric PMS known as biological aerosols, or bioaerosols, are made up of cellular components, bacteria, archaea, or fungal spores as dispersal units. Aerosols are considered dynamic systems because of the variety of substances and phases, solid, liquid, or gas, that they include 83. As a result, their particle size distribution ranges from the fine and coarse modes, 1m, resuspension aerosols, to the accumulation mode, 100 nm, indoor combustion aerosols from cooking, smoking, or incense burning, as well as the nucleation mode, 30 nm in vacuum cleaning conditions. Inhaling aerosols while indoors has been related to a number of harmful health impacts, mostly to the lungs, the human body's entryway, and other key target organs like the heart and brain. Radon soil gas, tap water, and building materials are the main sources of indoor radon. Radon is probably one of the components of the gas filling the pores in the soil because soil has trace amounts of radium. Regarding radon emissions from construction materials, radon can be released from any substance that contains even a trace quantity of radium. Since tons of masonry materials such as brick, concrete, and stone are used in the construction of buildings, they are the primary producers of indoor radon emissions among building materials. Using water from subterranean water sources that contain granite or other radium-bearing rock can emit radon inside. Radon concentrations in these water sources are often higher than 10,000 pci/L. And lastly, it's thought that radon within might also come from outside air. The major methods that underlying soil gas in buildings can contaminate people with radon are through permeation pathways. According to epidemiological research, the average amount of indoor radon can raise the risk of lung cancer by 3% to 14%. Chemical pesticides. These days, timber building materials are frequently protected by the impregnation or surface coating of both organic and inorganic pesticides. Additionally, bacteria, fungi, insects, rodents, and other species are among the pests that pesticides are used to manage and prevent. Pesticides in interior environments are often semi-volatile substances that can exist as gases or particles depending on factors including vapor pressure, product viscosity, and water solubility. Furthermore, research suggests that textiles and carpets may serve as long-term storage spaces for organic chlorine pesticides. According to the theory, pesticides in fibers from carpets, textiles, and cushioned furniture will migrate into polyurethane foam pads. As a result, throughout the course of their lifetime, carpets, textiles, and cushioned furniture may represent an integrated pesticide exposure. Furthermore, pesticides can infiltrate buildings through external openings. Since they are shielded from the sun, bitter cold, rain, and other elements once inside, they can survive for months or even years. The internal environment may expose people through the skin, food, and inhalation of pesticide-containing particles or volatile substances. Exposure to pesticides is linked to negative health effects, such as transient effects on the skin and eyes, headaches, nausea, and dizziness, and 2. Chronic long-term effects, such as diabetes, asthma, and cancer. Pollutants that are biological microorganisms such as viruses, fungi, and bacteria, as well as biological allergens like cockroaches, animal dander, cat saliva, house dust, and pollen, are examples of biological pollutants found in indoor environments. Biological allergens, often referred to as antigens, can come from a variety of plants, animals, insects, mites, or fungi. When particular immunoglobulin E, IgE, antibodies react with an allergen, an allergic reaction is produced. Allergens can come from both indoor and outdoor sources, although the most common indoor sources include furry pets, dog and cat dander, house dust mites, molds, plants, cockroaches, and rodents. Bacteria and viruses frequently come from or are transported by humans and animals. Exposure to biological allergens has been shown to cause wheezing, respiratory infections, sensitization, and respiratory allergic disorders, whereas indoor exposure to bacteria and viruses is likely to result in both infectious and non-infectious poor health consequences. IAQ standards and guidelines. It is clear that even at low air pollutant concentrations, prolonged exposure to indoor anthropogenic activities can degrade IAQ and pose serious health hazards to people. The scientific community and pertinent organizations have tried to create and implement IAQ standards and recommendations in order to address these IAQ issues. The international community finally established IAQ standards and guidelines based on an integrated building strategy after much work. The objective is to eliminate, or at least reduce, potential dangers to human populations. The WHO and USPA state that the purpose of the IAQ guidelines is to provide a crucial database as a reference for the prevention of detrimental impacts of IAP and preservation of public health. The WHO and USPA's IAQ standards for a few prevalent contaminants are summarized in Table 2. It is necessary to differentiate occupational standards, industrial, from non-occupational norms, residential residences, schools, and workplaces. The WHO and USPA standards often specify the highest values for particular times periods, e.g., 1 hour, 24 hours, or a year. Furthermore, as the WHO and USPA's IAQ guidelines are often applied for the control of IAQ within homes, schools, hospitals, public buildings, and workplaces, it appears that they are not applicable to occupational sectors. Each nation will also create unique criteria or norms that are appropriate for their own unique set of circumstances. Table 2 Indoor Air Quality Guidelines for Major Indoor Air Pollutants. The inherent oxidative potential of indoor air in indoor contexts, the oxidative capacity has been comparatively rarely investigated. The combination of indoor oxidants and their precursors shall be referred to as oxidants * in these research, which have recently begun to examine indoor oxidants and their precursors in atmospheric science. Major oxidants have been proposed to be ozone, O3, hydroxyl radical, O, and nitrate radical, NO3. Further noteworthy indoor oxidants * include hydrogen peroxide, H2O2, nitrogen dioxide, NO2, hydroperoxy radicals, HO2, chlorine atoms, Cl, and alkyl peroxy radicals, RO2. Since oxidation is thought to be the predominant process in indoor ozone reactions, the majority of studies on indoor oxidants * have only looked at ozone. It has recently been shown that one major source of indoor oxidants is the photolysis of nitrous acid, HNO, and the generation of O radicals by formaldehyde, HCHO. As a crucial species in photooxidation cycles in the atmosphere, the O radical can oxidize volatile organic compounds, VOX, to produce secondary aerosols or other gas species, which can have harmful and cancer-causing effects on people. Regarding the significant processes that lead to the generation of O radicals, these include, I. The reactions between NO and hydroperoxyl, HO2, 2. The reactions between ozone and alkenes, and 3. The photolysis reaction between ozone, 320 nm, HNO, 400 nm, and H2O2, 360 nm. The two main sources of indoor oxidant * emissions are electronics and building materials. In addition, both human and microbiological occupants may produce acetaldehyde and other carbonyls. Furthermore, human activities such as cooking, cleaning, vaping, smoking, disinfecting surfaces, and using air fresheners are likely to be significant sources of indoor oxidants *. Transport from outside and the production of secondary oxidants indoors are further significant causes. Increased O3/NO and O3/alkene reactions can result in elevated NO/HO2 and O3/O radical levels when there is greater outdoor to indoor transfer of O3 and NO. Leach J.A., 2024, Human Health Effects of Indoor Air Pollution. Building-related diseases. Decreased indoor air quality, IAQ, in homes and buildings has been connected to a number of symptoms and diseases in recent decades. Even at low concentrations, indoor exposure to inorganic, chemical, physical, and biological pollutants is frequent, pervasive, and prolonged. Consequently, there has always been a lot of concern and attention focused on the negative impacts of IAP on human health. Sick building syndrome, SBS, and building-related illness, BRI, are two major categories under which illnesses induced by indoor environmental factors fall under the umbrella of building-associated illness, according to the World Health Organization. Table 3 Building-related diseases syndrome of sick buildings, SBS. SBS is frequently used to describe a set of symptoms that are connected to the actual physical settings of particular buildings. Patients will experience acute health and comfort impacts of SBS after spending a specific period of time in a building, but it can be challenging to pinpoint both the effects and their causes. These effects can be found all over a building or restricted to specific sections. According to reports, symptoms often get worse the longer a person spends in a building and then go away when they spend more time outside of the structure. The WHO has classified SBS symptoms brought on by IAP into 4 groups: I. Irritation of the mucous membrane, causing irritation of the eyes, throat, and nose. 2. Neurotoxic effects, such as headaches, irritability, and exhaustion. 3. Asthma and symptoms similar to asthma, such as tightness in the chest and wheezing. And 4. Dryness and irritation of the skin, gastrointestinal issues, such as diarrhea, and other difficulties. IAP-associated SBS symptoms have been related to increased health risks for babies, the elderly, people with chronic diseases, and most urban dwellers of any age, according to the International Labour Organization, ILO. The chance of SBS prevalence is also generally increased by high room temperatures, moist buildings, and insufficient ventilation rates. Furthermore, the prevalence of SBS symptoms is significantly influenced by additional risk factors, including gender, atopy, and psychosocial factors. Diseases related to buildings, BRI. BRI identifies diseases and symptoms that are caused by exposure to indoor air quality problems and has a known causative agent. Chemicals including formaldehyde, xylene, insecticides, and benzene are recognized to be causal factors. However, biological agents are more common. Buildings with cooling towers, humidification systems, filters, drain pans, wet surfaces, and water-damaged building materials are common sources of indoor emissions of biological pollutants. The flu has been linked to BRI symptoms, which include fever, chills, tightness in the chest, pains in the muscles, and cough. Furthermore, significant respiratory and lung issues are probably going to happen. Legionnaire's disease, hypersensitivity pneumonitis, and humidifier fever are common BRI ailments. According to reports, there are 4 main ways that indoor environmental contaminants might lead to BRI symptoms: I. Immune stimulating, 2. Contagious, 3. Toxic, and 4. Irritating. The first insult that BRI frequently experiences is an irritating impact, but depending on the type of pollution and the individual's vulnerability, toxic, allergic, or infectious processes may develop later. Although psychological factors are frequently overlooked, it is known that they also raise the overall morbidity of diseases associated to buildings. BRI has been associated with 4 primary factors: I. Chemical factors, 2. Biological factors, 4. Psychosocial factors, and 3. Physical environmental elements. Regarding the physical environment, BRI can be affected by dust concentration, temperature, humidity, illumination, and air movement. On the other hand, the chemical factors encompass a range of contaminants emitted by human actions and goods, including paint, carpets, fresh furniture, cosmetics, asbestos, curtains, and insecticides. Finally, microbes are a crucial biological element linked to BRI. Severe respiratory illness: because pollutants enter the human body by breathing, the respiratory system is often the primary focus of IAP effects. Acute respiratory infections are divided into upper respiratory infections, URIs, and lower respiratory infections, ALRIs, based on the region of the respiratory tract that is afflicted. URIs are upper respiratory infections that are typically moderate in nature and are brought on by biological pollutants, viruses, bacteria, fungi, fungal spores, and mites. Common symptoms of urus include cough, sinusitis, and otitis media. On the other hand, viruses or bacteria produce ALRI, an acute lung infection, which causes lung inflammation. It has been discovered that IAP raises the risk of childhood ALRI by 78%, resulting in 1 million fatalities annually among children under the age of 5. Children's comparatively big lung surface area could be the reason for this. Research has shown that children who live in buildings that burn solid fuels have a 2 to 3 times greater chance of acquiring ALRI than children who live in buildings that burn clean fuels. IAP negatively impacts the respiratory tract's host defenses against infections, both specific and nonspecific. IAP also causes a high incidence of chronic bronchitis in cooking moms and increases the severity of respiratory infections. Heart conditions, allergy and pulmonary conditions such as atopic dermatitis, allergic rhinitis, and asthma are linked to inhaled air pollution. Furthermore, it is believed that smoking is one of the main risk factors for the emergence of long-term inflammatory pulmonary conditions, such as lung cancer, asthma, and chronic obstructive pulmonary disease, COPD. Exposure to IAP can have a substantial impact on the maximum amount of lung function obtained. As a result, lung function declines. PM and CO are two examples of harmful particles that might affect lung development early in pregnancy. Enhanced chronic inflammatory response in the lung and airways to harmful particulates or indoor air pollution is a characteristic of COPD disorders. It has been established that cooking smoke in the home increases the incidence of COPD in women, particularly in developing nations. PMS from burning fossil fuels cause inflammation in the lungs and significantly impair lung function. There is evidence that fuel smoke in the home can lead to COPD illnesses with symptoms and mortality comparable to those of tobacco users. Burning fuel produces chemicals with a high potential for oxidation, which lead to DNA damage and oxidative stress. These processes are thought to be the primary causes of the pathophysiology of COPD. Furthermore, biological elements including bacteria, viruses, and allergens have the potential to trigger severe inflammatory responses, immune system malfunction, and chronic inflammation, all of which increase the risk of COPD disorders. Exacerbations of asthma or symptoms of asthma may arise from indoor air pollution exposure. Acute exposure to combustion smoke has been shown to increase bronchial reactivity, cause inflammation and irritation, and is thought to be the primary cause of asthma exacerbations, particularly in youngsters. Research has shown that children aged 5 to 14 who reside in homes that burn coal, wood, or kerosene have a 1.6 relative risk of experiencing an asthma attack. Smoking is typically linked to lung cancer. Lung cancer is more common in women than in men in non-smoking cases, as evidenced by recent research showing a strong correlation between IAP exposure and long cooking sessions in women. Furthermore, data suggests that the percentage of female non-smokers who develop lung cancer varies significantly depending on the region. For example, smoking is unrelated to more than 80% of female lung cancer cases in East and South Asia, but it is just 15% in the United States. The burning of solid fuels for cooking or heating has been linked to significant lung cancer risk factors in terms of emissions. Research has shown that those who use solid fuels, such coal and wood, for cooking and heating throughout their lives are 4 times more likely to develop lung cancer than persons who use renewable energy sources. A number of gaseous and particle carcinogens, including as SO2, CO, NO2, POS, formaldehyde, heavy metals, and PM2.5, are substantially emitted during incomplete combustion. It has been discovered that these pollutants are linked to respiratory illnesses, morbidity and death, particularly lung cancer. Diseases of the heart, CVDs, solid fuel consumption in homes can release a number of pollutants, such as PM, POS, CO, heavy metals, and other organic pollutants, which have been connected to CVDs. Certain acute cardiovascular diseases, CVDs, such as ischemic stroke, myocardial infarction, cardiac arrhythmia, heart failure, and atrial fibrillation, are more common in people exposed to PM 2.5. According to reports, PM can lead to oxidative stress, systemic inflammation, elevated blood coagulability, and imbalances in the autonomic and vascular systems, which can result in CVD significant increases in fibrinogen, platelet activity, plasma viscosity, and the release of endothelins. A family of powerful vasoconstrictor molecules are also primarily caused by PM. Furthermore, the generation of carboxyhemoglobin by CO in indoor air is likely to affect tissue oxygenation, which has a significant effect on cardiovascular function. Furthermore, using fuel for cooking exposes people to Pa and PB, which increases oxidative damage, activates the renin-angiotensin system, and reduces nitric oxide. Peripheral vascular resistance and elevated vascular tone may result from these causes. Existing IAQ monitoring and control strategies, developing materials for IAQ sensors due to their distinct physical and chemical characteristics, two-dimensional, 2D, nanostructured materials have garnered a lot of interest in the last 10 years for their potential use in the development and manufacturing of gas sensing devices. It was shown that 2D materials had exceptional characteristics, including a high surface sensitivity, a big surface-to-volume ratio, and good semiconducting properties. Furthermore, combining two-dimensional nanostructured materials with three-dimensional materials is suggested as a viable method for creating high-performing IAQ monitoring sensors. It has been shown that 4 unique architectures for IAQ monitoring can be created by combining 2D nanostructured materials with 3D bulk materials, 2D nanostructures, 1D nanostructures, and 0D nanomaterials. 0D nanomaterials of nanoscale, 100 nm, size, such as quantum dots, QDs, nanoparticles, nanocrystals, and nanoclusters, have been used in the creation of photonic, electrical, and chemical sensing devices because of their unique optical and electrochemical capabilities. Many IAQ sensing applications have shown that 1D nanostructures, such as nanotubes, nanowires, NWS, nanofibers, and nanorods, work well when combined with 2D materials. This is because of their unique morphology, high surface-to-volume ratio, and quick electron transport. In the meantime, new forms of 2D heterostructures, such as black phosphorus/MOS2, graphene/MOS2, and graphene/WS2/graphene, have been employed in novel devices for IAQ monitoring due to the production of van der Waals heterostructures by the direct stacking of distinct 2D materials. Lastly, layered 2D nanostructured semiconductors can be merged with conventional bulk 3D semiconductor substrates in the creation of new gas sensing devices by growing or transferring 2D materials onto bulk 3D semiconductors. In conclusion, a variety of IAQ detection applications may benefit from the higher qualities of the constituent materials in heterostructure-based devices. Figure 7 Schematic overview of 2D nanostructured materials and different types of heterostructures with 0D, 1D, 2D, and 3D materials used for gas sensing applications. Reproduced with permission. One important tactic for IAQ monitoring has emerged: the creation of low-cost sensor networks and systems. Nowadays, metal oxide, MOX, sensors are thought to be among the best technologies because of their affordability, simplicity, high sensitivity, and compatibility with contemporary electronics. Their compact design and affordable price make them the perfect choice for portable and remote monitoring systems. Metal oxide semiconductor gas sensors have gained attention recently as a potential platform for the indoor air quality monitoring of CO and VOX. Several metal oxides have reportedly been used in IAQ sensing applications, including SNO2, ZNO, TiO2, IN2O3, Fe2O3, MoO3, CO3O4, CuO, NiO, and CDO. Cutting-edge technologies for IAQ monitoring. Many methods have been developed and made available for real-time monitoring. However, because of their expanding application in the Industry 4.0 revolution, wireless sensor networks, WSN, and Internet of Things, IoT, based systems are the most widely used technologies developed for IAQ monitoring. Systems based on the Internet of Things, IoT, with the growth of big data, the Internet of Things, IoT, and mobile technologies in recent years, machine learning technologies have emerged as popular ones with significant potential for real-time IAQ monitoring. The advent of portable IAQ monitoring devices powered by the Internet of Things has made it possible to readily monitor and manage air quality in real time these days. Numerous IoT-based IAQ monitoring systems and gadgets, including open-source data processing and transmission technologies, have been developed and released. Electronic noses, e-noses, which are biomimetic devices that imitate the functions of mammals' olfactory systems, are one of the significant uses of IoT in IAQ monitoring. A multi-sensor array, software with digital pattern recognition algorithms, an information processing unit, i.e., an artificial neural network, or ANN, and reference library databases are the four main parts of an e-nose system. Through the utilization of chemical sensor arrays and classification algorithms, e-noses can effectively monitor target gases by identifying and differentiating between various types and quantities. Because of this, e-noses have garnered a lot of attention due to its affordable, portable IAQ monitoring feature. For instance, Taston and colleagues presented the e-nose system, a low-cost, portable, Internet of Things, IoT-based, real-time monitoring tool that uses a variety of sensors to assess various air pollutants, including CO2, CO, PM10, and NO2, as well as air characteristics, such temperature and humidity. In particular, the suggested e-nose is created using four detection units: the GP2Y1010O dust sensor, the MHZ14A CO2 sensor, the MICS4514NO2 and CO sensor, and the DHT22 temperature and humidity sensor, as well as open source, inexpensive, and simple to install software. These sensors use the 32-bit ESP32 Wi-Fi controller for monitoring, and data is received and stored in a cloud server by a mobile device interface built on the BLYNK IoT platform. It is predicted that future IAQ monitoring devices will be modeled after this idea. Chen et al. Conducted additional research and created a high-performance smart e-nose system that includes a wireless data transmission unit, a mobile phone receiver, a readout electronic circuit, a multiplexed tin oxide, SNO2, nanotube sensor array, and a data processing application. Because this nanotube sensor uses sensors with a large surface area for gas molecule interaction, it has superior sensitivity for gas detection and discrimination at room temperature when compared to traditional devices. This e-nose device can be considered to have state-of-the-art sensitivity for air pollutant detection at room temperature based on metal oxide sensors, because it was shown to be able to detect indoor target air pollutants using only a basic vector matching recognition algorithm. Consequently, it is significant that the smart e-nose system and device can be used for high-performance indoor environment quality monitoring in smart homes, smart buildings, or even smart cities in the present and the future. Figure 8: a smart ventilation system for maximizing indoor air quality, IAQ, levels in buildings. D. An illustration of the suggested electronics nose, e-nose, system architecture. A potential e-nose application in future smart buildings. B. And a crude concept design of smart air. C. Used by permission. Recently, cloud computing and Internet of Things, IoT-based smart devices have been created to effectively communicate real-time data to an IoT sensor network and precisely monitor IAQ. Three parts make up the smart air device: an LTE modem, a microprocessor, and an array of sensors for detecting pollutants. A temperature/humidity sensor, a CO2 sensor, a laser PM sensor, a VOC sensor, and a CO sensor are among the sensors in the smart air gadget. In addition, the smart air platform uses Internet of Things and cloud computing technologies to monitor and manage IAQ anywhere, at any time. Crucially, testing conducted by the Korean Ministry of Environment has shown how dependable the device is. All incoming data is kept in the cloud of the web server to provide resources for additional IAQ analysis. A recently established technique for IAP reduction using demand-controlled ventilation systems, DCVs, based on CO2 sensing is based on the concept of combining ventilation system activation with IAQ variable level detection. The IAQ index computation, mobile app, backend, and hardware make up the four main parts of the system. In order to precisely and automatically operate the ventilation system and maintain an appropriate concentration of air pollutants by balancing indoor and outside factors, the system's functioning depends on a number of real-time sensors and algorithms. Using recorded data, a sensing platform offers an Internet of Things, IoT-based solution for controlling a building's IAQ levels. A number of variables are measured simultaneously, including temperature, humidity, VOx, and CO2 in both the indoor and outdoor environments. This information is then used to calculate the IAQ index, which is a tool for algorithm-based ventilation control. The solution also enables management and inspection through a mobile app. Systems based on wireless sensor networks, WSNs, the wireless sensor network, WSN, has drawn a lot of interest in the last several years from a variety of monitoring scenarios. WSN is often made up of small units, or nodes, that play a crucial role in wirelessly interacting with other nodes in the system and gathering data from sensors in the surrounding area. ZigBee, a wireless standard based on the IEEE 802.15.4 specification, has been said to be the most dependable communication protocol in the development plans of the WSN system due to its low cost, low consumption, and low data rate. Furthermore, networks operating on the ZigBee protocol can operate in power-saving mode. WSN systems are typically used in conjunction with a distributed sensor network that is linked to a cloud system. Through a gateway, ZigBee-based sensor nodes send field measurement data to the cloud system. The collected data from the sensor network has frequently been processed, stored, monitored, and visualized using the cloud computing technologies that have been optimized. In order to optimize the detection of air pollutants, artificial intelligence techniques are also utilized to process and analyze the acquired data. The huge number of nodes set up to offer pertinent data on the distribution of IAQ in various locations means that WSN systems have the potential to greatly improve air quality monitoring and measuring efficiency. The WSN is an automatic IAQ monitoring system that provides real-time data to the user or building manager. It measures IAQ in various regions autonomously, accurately, and simultaneously. It has been discovered that WSN systems are typically used for temperature, relative humidity, CO2, luminosity, and a number of common volatile organic compounds, VOx, including benzene, ethylbenzene, toluene, and xylene. Technologies for air purification to improve IAQ. The development of air purification technology, optimization of ventilation systems, and control of emission sources are seen to be the three primary strategies for enhancing IAQ. The exploration of innovative technologies for the purpose of filtering and purifying indoor air contaminants has garnered significant attention in the past 10 years. The most advanced methods for eliminating gas contaminants have long been recognized to be adsorption processes employing carbon-based filter medium. Numerous HVAC filters, both residential and commercial, have been produced and are utilized in a variety of facilities, including homes, shopping centers, schools, and office buildings. Adsorptive HVAC filters have been shown to be able to efficiently remove a number of harmful pollutants, such as PM, aerosols, O3, and VOx. HVAC filters come in a variety of configurations, including cartridges filled with granulated activated carbon or bag filters, and filter cassettes composed of flat sheet filter material. Vin Van Tran, 2020, Technologies for Air Purification to Improve IAQ. The development of air purification technology, optimization of ventilation systems, and control of emission sources are seen to be the three primary strategies for enhancing IAQ. The exploration of innovative technologies for the purpose of filtering and purifying indoor air contaminants has garnered significant attention in the past 10 years. The most advanced methods for eliminating gas pollutants have long been recognized to be adsorption processes with carbon-based filter medium. Numerous HVAC filters, both residential and commercial, have been produced and are utilized in a variety of facilities, including homes, shopping centers, schools, and office buildings. Adsorptive HVAC filters have been shown to be able to efficiently remove a number of harmful pollutants, such as PM, aerosols, O3, and VOx. HVAC filters come in a variety of configurations, including cartridges filled with granulated activated carbon or bag filters, and filter cassettes composed of flat sheet filter material. However, due to a large decrease in its equilibrium adsorption capability at sub-ppm concentrations of contaminants, this technology has demonstrated a severe limitation with respect to adsorption efficiency. Furthermore, it has been shown that the presence of humidity significantly lowers the adsorption efficiency of carbo-N-based filters. Therefore, one possible strategy for the development of HVAC filter development plans is to enhance the air filter system's long-term operation and performance. Extended use can encourage the growth of bacteria and mold, which effectively reduces the effectiveness of the air filters. It has been shown that non-thermal plasma, NTP, technologies are an efficient way to deal with these issues. The production of a quasi-neutral environment, such as radicals, ions, electrons, and UV photons, provides the foundation for the functioning of NTP approaches. Numerous non-thermal discharge plasma methods, such as surface discharge, dielectric barrier discharge, and corona discharge, have been developed for the purpose of eliminating indoor air contaminants such VOx, SOx, and NOx. It has been demonstrated that the air filter can act as an efficient electric precipitator because of electrostatic force, and that the ozone produced by the electric discharge demonstrates a notable germicidal power. NTP methods do have certain drawbacks, though, I. Low energy efficiency, 2. Performance is significantly impacted by humidity, and 3. Secondary hazardous emissions, like CO, HCHO, and NOx, can occur. The technique's practical applicability for indoor air filtration have been hindered by these disadvantages. Advanced oxidation processes, AOPs, based technologies have garnered significant attention in developing strategies for controlling indoor air pollution since they produce the least amount of secondary pollution. Among these, photocatalysis, the technique of subjecting semiconductor photocatalysts to sufficiently intense irradiation to cause them to disintegrate, has been seen as a potential technology. When compared to traditional adsorption methods, photocatalysis has a number of notable advantages. Under ambient conditions, the direct breakdown of gaseous pollutants, especially volatile organic compounds, VOx, into CO2 and H2O, and 2. The suitability of this process for the removal of low-concentration pollutants, sub-ppm levels. In photocatalysis technology, semiconductors such as titanium dioxide, TiO2, graphitic polymers, tungsten oxide, WO3, carbon nitride, CN, Ag, cadmium sulfide, CDs, metal oxides, MOX, M equals Fe, Zn, V, perovskite, and others are utilized as photocatalysts. However, TiO2 has drawn increased attention for IAP purification because of its strong oxidative power, low cost, and chemical stability. IAQ control in a smart home, the smart home in particular, as well as home automation in general, have garnered a lot of attention lately. These days, a key component of smart cities is the smart home, which can be managed by wearable technology and smartphone applications. The suggested home energy management system served as its cornerstone, HEMS. Actually, the original purpose of the smart home's development was to maximize ventilation technology and increase energy efficiency. Currently, nevertheless, the term smart home is most frequently linked to a variety of home automation systems, including devices for entertainment, communications, and appliances. Future advancements in smart home technology are anticipated to go in two main directions: I. The previously mentioned control over blinds, appliances, and ventilation to save energy costs and improve comfort, safety, and health, and 2. Helping the elderly and disabled through the use of robotic devices and smart sensor technologies. The smart home does, however, also present chances to lessen the detrimental effects of IAP on people's health. Undoubtedly, IAQ and air hygiene will receive more attention as smart home technology is implemented in buildings more frequently. The three primary parts of a typical smart building system are the controller and devices, the power supply media, and the user gateway media. User gateway media, which combines a supervisory control and data acquisition, SCADA, interface with a smartphone application, enables residents to remotely monitor and operate appliances from computers or smartphones via Wi-Fi or a wireless module. Using renewable energy sources, power supply media is a revolutionary technology that maximizes energy efficiency. Lastly, the temperature, air pollutant concentrations, and fan speed are automatically controlled by the controller and devices. These days, sensor technology is the key to smart buildings. All meteorological parameters and pollutant concentrations are automatically and continuously recorded in the SCADA system through the use of various sensors. Smart sensor systems can specifically take necessary action, e.g., modify temperature and/or ventilation settings, to improve IAQ and lower IAP based on the data captured by them. In summary, indoor air pollution has a major role in the development of human diseases. PM, VOx, CO, CO2, ozone, radon, heavy metals, aerosols, pesticides, biological allergens, and microorganisms are just a few of the many indoor air pollutants that can lower IAQ and have a negative impact on people's health. The primary sources of the majority of these pollutants are often human activities occurring within buildings, such as cleaning, combustion, the use of specific building materials during construction or renovation, and the use of electronic equipment, and 2. Transportation from outside sources. Even though these pollutants are frequently found in buildings in very small amounts, prolonged exposure to them can have serious negative effects on health. Sick building syndrome, SBS, and building-related illness, BRI, are the two main classifications of building-associated illnesses. Numerous tactics and methods for regulating and lowering pollutant concentrations have been implemented in an effort to lessen the effects of IAP. It is anticipated that the creation of sophisticated sensor materials, IAQ monitoring systems, and smart homes will prove beneficial for IAQ regulation and improvement in the future. Vin Van Tran, 2020, Thermal Comfort and Lighting Design. The contentment of residents with the thermal surroundings is referred to as thermal comfort. Among the variables affecting thermal comfort are impacts the interior temperature environment. There are three basic ways that heat is exchanged between the human body and its surroundings: radiation, convection, and evaporation. Both internal and exterior factors can impact the temperature of an indoor space. Typical heat sources include electrical devices, such computers and lights. Solar radiation and human existence. Typical chilly sources include window surfaces, walls with inadequate insulation, thermal bridges within the building. Thermal comfort influencing factors. 6 different factors primarily affect thermal comfort, and maintaining a good balance between them is necessary to keep occupants satisfied with their surroundings. Air temperature is a frequent factor in thermal comfort and is easily regulated by mechanical and passive heating and cooling systems. The weighted average temperature of all exposed surfaces in a room is known as the mean radiant temperature. It is possible to define the operating temperature, the most crucial element of thermal comfort, when combined with the air temperature. The speed and direction of the air motions in the space are measured by air velocity, also known as airflow. Draft complaints could be caused by abrupt changes in air velocity. The amount of moisture in the air is called humidity, or relative humidity. Uncomfortable humidity levels might result from being too high or too low. The degree of insulation that clothing adds to a person's body. Wearing more clothing will decrease the amount of heat lost via the skin and the temperature that is considered comfortable. The degree of physical activity, also known as metabolic heat, affects how much heat the body produces and, consequently, how hot or cold an environment seems to be. In actuality, the following variables are impacted by the type of ceilings being used: air temperature, since in the case of tabs, it might be affected by how the ceiling permits the air to cool as it comes into touch with the slab. Mean radiant temperature, since it may be affected by the ceiling's radiant panel coverage ratio. Air velocity, which can be influenced by how absorbers are arranged and how big the air gaps are between panels, allowing convection to happen. M. Frunzak, 2011, Acoustic Considerations. The effects of noise pollution on one's general well-being, productivity, and health can be profound. The following design techniques can enhance acoustic comfort: zoning, room geometry, and sound insulation. Designers can build environments that encourage concentration, relaxation, and communication by taking into account acoustic comfort. Acoustics, which includes sound absorption in different rooms and spaces as well as sound insulation of external and internal noise sources, is a crucial factor to take into account in residential buildings. 7 Acoustic factors to take into account while designing a home. Noise is a significant consideration when planning and developing residential buildings. Residential building design is regulated by legislation to guarantee that residents can go about their everyday lives, including resting and sleeping, without being disturbed by other properties. Limits on the amount of external noise intrusion that is permitted can also be imposed by planning conditions. The issue of sound propagation in residential structures. A good acoustic design must take into account a variety of sound transmission routes. Certain types of airborne sound transmission, such those that pass through windows or a floor that divides apartments, are simple to locate and reduce. Flaring transmission also refers to other channels of transmission, such as sound transmitted through pipes or horizontally under a shared floor slab beneath a dividing wall. These are frequently far less evident and can go unnoticed without the assistance of a qualified acoustic specialist. This is particularly true when creating residential homes inside of an existing structure, as there may be several undiscovered transmission pathways nearby. Important things to think about when building residential buildings. While some acoustic factors must be taken into account during the planning phase, others must be approved by the building regulations. While certain developments provide greater challenges than others, taking into account the following factors will usually guarantee that your construction meets all acoustic regulations and provides future occupants with a high caliber of acoustic amenity. Ground-borne noise, vibration, and locations near vibration sources like train lines that may cause audible vibration or noise transmission. Because installing mitigation to minimize ground-borne vibration into a building is extremely difficult to do and very expensive, vibration measurements can help identify possible areas of issue early on. Insulation against airborne sound within. To lessen the transfer of airborne noise between rooms and adjacent properties, appropriate acoustic insulation is needed between floors and walls. The building regulations approved document E governs the performance standards. A higher level of sound insulation could be necessary when a private home and a business property share a dividing feature. Impact sound insulation inside it is important to take practical steps to lessen impact noise. The building regulations regulate the minimum performance requirements, just like they do for airborne sound insulation. Control of reverberation requirement E3 of the building regulations, which limits the quantity of echo, or reverberation time, in social areas of residential structures, is one area that is frequently disregarded. This is a developing issue that is partly brought on by the move away from carpets and soft furniture. It is crucial that the right surface treatments are used in the design from the beginning. Noise from inside building services. It is important to manage noise produced by mechanical equipment, such as air conditioning systems, mechanical extract ventilation, MEV, and mechanical ventilation heat recovery, MVHR, to keep it from becoming an annoyance. The increasing demand for new homes to reduce overheating has led to the integration of mechanical ventilation or cooling systems. Evidence, however, indicates that residents will choose not to use the systems if the equipment is excessively noisy, so eliminating any potential benefits. Outside noise from building services planning clearance is typically required for new equipment connected to residential constructions, such as air conditioning condensers and certain air source heat pumps, ASHP. This calls for measuring the background sound levels that now exist, forecasting the noise from the new equipment to travel outside adjacent properties that are sensitive to noise, and, if necessary, designing acoustic enclosures, barriers, or other noise control measures. Hammersmith, 2021, Biophilic Design and Well-Being. In order to improve occupant well-being, biophilic design incorporates natural elements into the built environment. This method can incorporate natural elements, views of nature, and natural patterns and acknowledges the innate human connection to nature. A comparative study between sustainable architecture and biophilic design. This section focuses on the particular issues with sustainable building that biophilic designs can help with. From the 17 Sustainable Development Goals, SDGs, UN, 2015, we examine the idea of sustainable architecture. Here, sustainable architecture acts as a lens to show how biophilic design helps to realize the objectives of sustainability in architecture. We compile the several advantages of biophilic design that have been covered in previous research and contrast them with the sustainable architecture issues that are grouped into the 17 goals. Additionally, we list the most important biophilic design components for the suggested biophilic design framework in this challenge-benefit analysis. We also talk about the potential for creating multi-benefit solutions. The context of biophilic design. One of the pioneers of biophilic design, Kellard, 2008b, p.3, describes it as a deliberate attempt to improve people's physical and mental health, productivity, and well-being, and to satisfy the need of contact with natural systems and processes in the contemporary built environment. He contends that biophilic design has the potential to promote positive human-nature interactions and have a positive environmental impact. Joan, 2022, in summary, promoting healthier and more productive settings requires an understanding of and commitment to enhancing indoor environmental quality through efficient management of air quality, thermal comfort, lighting, acoustics, and biophilic features. Investing in IEQ improves the sustainability of built environments and contributes to occupant well-being. Chapter 7, Water Management in Building Design. Designing buildings with efficient water management in mind is essential to environmental preservation and sustainability. In order to maximize water consumption, reduce waste, and safeguard water quality, architects, engineers, and builders can employ a variety of tactics and methods that are covered in this chapter. 7.1 Sustainable water use practices. Using water-efficient appliances, installing low-flow showerheads and toilets, quickly repairing leaks, and adopting water-saving practices like turning off the tap while brushing your teeth and gathering rainwater for your garden are some methods for cutting down on water wastage in residential settings. By implementing effective water management systems, recycling and reusing water, investing in water-saving technologies, and regularly conducting environmental impact assessments to reduce pollution and water waste, industries may assure sustainable water use. Rainwater collecting is another sustainable way to augment their water supply. By collecting rainfall from surfaces and roofs to supplement water supply and lessen dependency on surface or groundwater sources, rainwater harvesting helps promote sustainable water use. By reusing collected rainwater, this technique encourages water conservation while reducing the strain on the current water system. Individual water footprints can be greatly decreased by making little changes to consumption patterns, such as sealing leaks, installing water-efficient appliances, taking shorter showers, and collecting rainwater for gardening. When taken as a whole, these initiatives lessen the demand on freshwater resources and advance a more sustainable water management framework. Ivana, 2024, Rainwater harvesting and greywater recycling. Rainwater collection and greywater recycling are two effective ways to reuse water and reduce the demand on municipal water supplies. However, there are a number of noteworthy differences between the two approaches that could affect how well they work in certain situations. Gray water may contain contaminants like soap, detergents, and bacteria, which results in a lesser quality than rainwater. While rainfall can typically be used without treatment for non-potable uses, gray water requires more extensive treatment before it can be reused. When it comes to rainwater harvesting, local rainfall patterns and roof size are often more important factors than gray water recycling, which is determined by the amount of wastewater a family produces. However, rainwater collecting can provide more water than gray water recycling during periods of heavy rainfall. The choice between rainwater harvesting and gray water recycling will depend on a number of factors, including the local temperature and rainfall patterns, the availability of water resources, and municipal legislation governing the use of reclaimed water. Homeowners and companies should carefully consider these problems before deciding which technique to employ. In general, rainwater collection and gray water recycling are both excellent strategies to minimize water usage and preserve water resources. The optimal approach will vary depending on the requirements and situation of each user. Reagan, 2024, Stormwater Management Techniques. EPA facilitates stormwater management practices at its sites. EPA practices sustainable stormwater management, often known as low-impact development, LID, or green infrastructure. The goals of sustainable stormwater management are to enhance water quality and lessen runoff. Through site grading, vegetation, soils, and organic processes that absorb and filter runoff on site, LID methods contribute to the maintenance of natural hydrologic cycles. Additionally, they lessen water pollution, flooding, and erosion downstream of EPA sites. Verdant roofs. In order to facilitate rainfall infiltration and the evapotranspiration of stored water, green roofs are covered in flora. In addition to lowering energy expenses and the heat island effect, a green roof can also improve the aesthetics of the surrounding area and lessen the effects of air pollution. Green roofs are a feature of the EPA's New England Regional Office in Boston. To irrigate the green roof, rainwater is gathered from the rooftops of the 4th, 5th, and 17th stories, held in cisterns, and then dispersed by a solar-powered pump. There is an 8,000 square foot green roof at the Andrew W. Breidenbach Environmental Research Center in Cincinnati, Ohio. There is 1,000 cubic feet of water storage capacity on the roof, which is sufficient to hold onto 1.6 inches of rain from a storm. In addition, the Atlantic Coastal Environmental Sciences Division of the Environmental Protection Agency in Narragansett, Rhode Island, and the agency's headquarters in Denver, Colorado, and Seattle, Washington, have green roofs. Pavements with permeability. Unlike impermeable surfaces like concrete or asphalt, permeable surfaces allow precipitation to seep into the groundwater and soil through porous surfaces. Pervious concrete, porous asphalt, pervious interlocking concrete pavers, or grid pavers are examples of EPA parking lots, driveways, or sidewalks. At its Region 2 laboratory in Edison, New Jersey, the EPA constructed a 300,000 square foot permeable pavement parking lot with pervious interlocking paver blocks, porous asphalt, and porous concrete in order to study the effects of various permeable surfaces on stormwater runoff. Areas for bioretention. Shallow, planted depressions known as bioretention areas allow runoff to collect in a specific location and subsequently filter through the surrounding soil and vegetation. Rain gardens are another name for small-scale bioretention sites. At the Environmental Science Center in Fort Meade, Maryland, EPA staff members assisted in creating a rain garden using native wildflowers and grasses. Rain chains direct rainfall into the garden from the roof gutter. Dry and vegetable swales. Swales are vegetated channels or drainage routes that move water. They can be utilized in place of concrete open channels or subterranean storm sewers in small drainage areas with little flow. As runoff moves through the system, wetlands aid infiltration, and runoff slowing. Gutter and curb removal. Rainwater is swiftly collected and sent to a stormwater drain by curbs and gutters, preventing infiltration and the removal of pollutants. Runoff can be channeled into pervious areas and filtered through lid features by removing curbs or adding curb cuts. Swales are an additional option for conveying runoff in place of curbs and gutters. Strips of vegetable filters runoff is diverted through extensive belts of vegetation known as vegetated filter strips. The greatest places for them are those with gentle slopes and little chance of channelist flow. Filter strips can handle impermeable surfaces, roof downspouts, extremely tiny parking lots, and run off from roads and highways. Filters made of organic materials and sand at the EPA's Region 7 office in Lenexa, Kansas, runoff is channeled to filters and a created wetland where it infiltrates via a sand bed to eliminate contaminants, floatables, and particle metals. In order to filter pollutants out of storm water before it is released into receiving waters, groundwater, or for reuse, they are usually utilized as part of a treatment train. Built-in wetlands. Artificial wetlands are replicas of natural wetlands. They produce a variety of habitats for wildlife and collect and filter runoff. They are intended to hold water that is saturated slightly below the soil surface or standing water on the surface. Riparian buffers. An region beside a stream, wetland, or coastline where development is limited or forbidden is known as a riparian buffer. The main purpose is to physically divide the aquatic region and keep it safe from further disturbance or encroachment. When a buffer is built correctly, it can function as a right-of-way during floods, protecting aquatic habitats and ecosystems. Anonymous, 2023, Water Quality Considerations. The possibility of a negative aspect to the economic progress brought about by the decades of fast industrial growth that followed World War II became apparent in the 1960s. The public started to learn about the repercussions of handling waste materials improperly and industrial mishaps at this time. Terrifying events at Love Canal, Sevso, and Bhopal during the 1970s and 1980s had catastrophic consequences for the general populace outside the facility's perimeter. The general public's understanding of numerous other significant environmental challenges has increased during the last few decades: acid rain and global warming, or the greenhouse effect, depletion of ozone in the stratosphere, tropical deforestation, the problem of urban litter, pesticides in groundwater, and the disposal of hazardous waste, both man-made and natural carcinogens. The emphasis on environmental factors has moved from a single medium, air, water, and land, to a comprehensive approach. Prior laws allowed countercurrent air stripping to be used to remove a solvent, such as trichloroethane, methylchloroform, from contaminated groundwater. It was quickly discovered that although the water was now clean, the process had produced an air pollution. The fact that transferring a pollutant from one medium to another does not solve the issue is addressed by today's rules. In the aforementioned case, the solvent extracted from the water needs to be recovered or burned after being condensed or adsorbed by activated carbon. Recognizing that only industrial wastes that are eliminated or converted into environmentally friendly products at the municipal treatment plant should be disposed of in city sewers is another development. Wastes from industries that degrade the quality of effluent water or make sewage sludge dangerous need to be handled in a way that is acceptable to the environment. All parties involved must put in consistent, long-term effort to achieve this aim. Pollution control and waste management are now included in the cost of making a product. Making a contaminated waste stream appropriate for disposal is frequently more expensive than changing processes to produce less trash or more benign wastes and to recover useful components from waste streams. The usage of water in industry. Fresh water is a vital resource that needs to be conserved, used responsibly, and managed. This is becoming more and more clear. Even while water covers 2/3 of Earth's surface, the majority of that water is saltwater, which is not easily utilized for most purposes. Rainfall either seeps into the ground or flows off into rivers and streams to provide all fresh water. Chapter 1 demonstrates the dynamic nature of the hydrologic cycle. To guarantee a sufficient amount of superior quality water for industrial purposes, the subsequent measures need to be put into effect: cleaning and conditioning before being used for industrial or consumer, potable, purposes, preservation, and, when feasible, reuse, wastewater treatment. In industrial applications, cooling systems are being adjusted to utilize less fresh water makeup. Reusing waste streams, such as municipal plant effluent for cooling tower makeup, and operating cooling towers at high cycles of concentration can both greatly cut water use. Inadequate waste management can lead to pollution of surface and groundwater resources. Sharing resources is still necessary because of the rising demand for fresh water. All residential and commercial wastewaters must be treated more thoroughly in accordance with regulations in order to eliminate environmental and industrial pollutants and get the effluent water back to the level needed by the final user. In addition to controlling more traditional contaminants like ammonia, nitrates, and biological oxygen demand, facilities that handle household waste must also adjust the pH if it falls outside of the neutral range. There is a general concern regarding the safety of drinking water sources. Although a variety of contaminants, including those found in nature, can harm water quality, industrial activity, and the use of fertilizers and pesticides in agriculture are the main causes of the problems that the public is most aware of. Environmental regulations set quality standards for releases of treated household and industrial trash. Global adoption of stricter pollution control standards is likely to occur in the next years, despite the fact that certain nations have more extensive laws and permit rules than others. The quality of the air. The wines are not aware of geographic limits. The complexity of air quality concerns stems from the fact that they typically involve multiple countries. Important problems like acid rain, the greenhouse effect, and stratospheric ozone depletion demand a level of worldwide cooperation that is challenging to attain. Modern technologies can positively and quantifiably affect these problems. This handbook's several chapters cover technology that improve the effectiveness of industrial and boiler cooling. For significant energy consumers such as refineries, steel mills, power plants, and paper mills, every small improvement in energy efficiency means less fuel being used. Less carbon dioxide is created when fuel use is decreased, and where coal or other fuels containing sulfur are utilized, there is the quantity of energy needed to perform electrostatic particle precipitation and wet scrubbing, to remove acid gases, is one issue that governments deal with. The total energy released by burning coal is used in these processes to the tune of up to 30%. Although these methods lessen the pollutants believed to be the source of acid rain, they also burn more coal, which increases the amount of carbon dioxide produced, one of the gases believed to be the cause of the greenhouse effect. The utilization of alternative energy sources, such as nuclear fission, and at some time, possibly nuclear fusion, geothermal, wind, hydroelectric, photovoltaic, biomass, and solar, might significantly reduce a number of the air pollutants of concern. Many of the alternatives now come with their own set of drawbacks and are far more expensive than using fossil fuels. No straightforward answers exist, and no energy source that is both environmentally benign and commercially viable has been created. The majority of developed nations have enacted legislation in recent years to address issues with air pollution and emissions from power plants and industries. To address global atmospheric problems, nations have started to work together to develop accords and protocols. A global accord has been reached to gradually discontinue the use of specific chlorofluorocarbon compounds, which are employed as refrigerant gases and for other purposes. This is due to their association with a decrease in ozone levels in the stratosphere. There is reason to think that when stratospheric ozone levels decline, more UV radiation will be able to reach the Earth's surface. This will likely have unfavorable impacts such as raising the incidence of skin cancer. There are efforts to create international accords that offer incentives to developing nations so they can advance economically without destroying their rainforests. In addition to being important for conservation, the rainforests mitigate global warming and the greenhouse effect because they extract large amounts of carbon dioxide from the atmosphere through photosynthesis. The state of our knowledge about atmospheric chemistry is still very incomplete. There will surely be numerous shifts in focus and direction regarding atmospheric contaminants as our understanding expands. The extent and severity of industrial air pollution laws will keep rising because industrial activities and electricity generation contribute significantly to atmospheric pollution. Reduction of industry waste and energy conservation. Throughout the 20th century, developed countries transitioned from being abundant resource explorers to resource guardians. Natural resources seemed endless and industrial product consumption was low in the early 1900s. The limitations of Earth's natural resources became a growing issue as the demand for industrial products and electricity increased. Even developing nations are becoming increasingly interested in managing the development and use of their resources. Industrial producers now have to take into account the following goals in addition to achieving the intended output at a specific cost: to utilize as little energy and raw materials as possible, to reduce waste by using resources efficiently, to recover valuable materials from production waste, and to treat any leftover waste so that it can be transformed into an environmentally acceptable form before being disposed of. There are several worries concerning trash disposal methods in addition to the loss of natural resources. It is no longer acceptable to bury untreated industrial waste, regardless of its classification as hazardous or non-hazardous. The method that is currently allowed by the majority of nations is the landfilling of stabilized residues from industrial wastes that have been burned, heated, or subjected to biological oxidation or degradation. It is possible to recover some materials that are waste products from one process and repurpose them in another. For example, boiler blowdown can occasionally be utilized as cooling tower makeup. It is possible to recover valuable components from other waste products. It is now economically feasible to use alternative raw materials and modify processes to produce less trash, particularly hazardous waste, as the cost of disposing of waste has increased. There is a growing demand to treat waste and wastewater so that they can be productively utilized. The market is the most effective factor in selecting waste-reducing alternative raw materials and procedures. Certain procedures might offset greater starting costs with lower operational expenses due to the high cost of waste treatment and disposal. In contrast to ion exchange systems, membrane systems, such as reverse osmosis and electrodialysis reversal, have been effectively employed to treat boiler makeup water and lower the overall amount of contamination in the waste discharge. The total amount of wastewater has also been decreased by the use of membrane treatment for cooling tower blowdown. It is now possible to recycle process condensate streams as boiler feedwater by removing ammonia and carbon dioxide from them. The utilization of side cooling towers reduces blowdown. While international efforts are underway to guarantee that industrial wastes are appropriately managed, the expense of repairing the harm caused by previous practices needs to be considered as well. In the past, careless disposal of industrial wastes has led to serious groundwater contamination, leaching, issues. The public is very concerned about this type of contamination since it is very hard to monitor and follow the subsurface flow of chemicals leaching from dumping places. The majority of people on the planet get their drinkable water from wells or springs that are fed by groundwater. An aquifer's turnover might take years or even decades, so any contamination could be dangerous. Fortunately, leaking pollutants may be broken down into harmless molecules by some natural processes, such as microbial digestion. Adding specific nutrients and inoculum cultures to contaminated soils to hasten the biological breakdown of contaminants is one therapy that is gaining traction. There are numerous helpful variations of this procedure, which is known as bioremediation. It is the responsibility of industrial and commercial firms to reduce their use of the planet's natural resources and to produce the least amount of waste and pollution possible. Every country now understands that environmental conservation is a pressing and continuous issue. Redesigning industrial processes to reduce waste production will require a significant investment of time and energy. Treatments for deposits and corrosion that are both environmentally friendly and effective in harsh environments are essential. Systems for feeding, handling, controlling, and maximizing system performance with the least amount of environmental effect require efficient systems. Biro, 2024, building designers may considerably improve the built environment's resilience, cut down on resource consumption, and promote environmental sustainability by using these water management techniques. In addition to helping individual projects, This all-encompassing strategy promotes neighborhood projects and the ecological health of the area. Chapter 8, Waste Management and Recycling in Construction. Reducing the environmental effect of construction activities and encouraging sustainable practices in the sector depend heavily on efficient waste management and recycling. This chapter examines a number of waste management topics, such as the different kinds of waste that are produced, waste minimization techniques, recycling opportunities, and environmentally friendly disposal methods. 8.1 Construction and demolition waste. The materials produced during the construction, renovation, and demolition of buildings and infrastructure are referred to as construction and demolition, C&D, waste. Trash resulting from the construction, remodeling, repair, and demolition of homes, major buildings, roads, bridges, piers, dams, and other structures is known as construction and demolition, C&D, trash. Wood, steel, concrete, gypsum, masonry, plaster, metal, and asphalt make up C&D trash. Table 4 summarizes the type of waste. Legal classification, anonymous, 2020, C&D garbage frequently makes up a sizable portion of landfills. Nonetheless, a large portion of this garbage can be redirected for recycling or reuse if the proper tactics are put in place, reducing its environmental impact. Strategies for minimizing waste. By preventing trash from ending up in a landfill, reducing waste on a building site benefits your company financially and contributes to environmental preservation. You can limit the quantity of waste generated by your construction, renovation, or demolition site by implementing a number of preventive measures. Take into account these steps to cut down on waste at a construction site. In order to reduce waste in the construction sector, projects must be carefully planned, carried out, and monitored. Important tactics consist of: a well-thought-out design can minimize waste generated by a project by utilizing less material and creating uniform designs that minimize surplus offcuts. Ordering efficiently prevents superfluous materials by precisely measuring and ordering everything. Regular inventory counts help you avoid purchasing more. Purchase directly. 10% or more of building waste is packaging trash. While packaging is necessary to preserve commodities, buying in bulk from suppliers directly provides an alternative to wrapping each item individually. Reduce errors. When mistakes happen on building sites, resources get damaged and become unusable, which results in waste. The majority of these will be accidents, but it's crucial to do a risk assessment and employ qualified, competent workers, and supervisors, if applicable, to lower the likelihood of errors. Safe storage lowers the possibility of damage, which can render your goods worthless by shielding them from the elements, possible theft, and vandalism. If at all possible, this should be in a secured, covered container. Recycling bins. Make sure that bins and storage containers are positioned in a convenient location near the location where garbage is produced on your construction site. Employees can more easily sort rubbish and place it in the appropriate recycling container thanks to this. Anonymous, 2024, 8.3 Recycling and reusing building materials. In order to reduce waste in the construction sector, projects must be carefully planned, carried out, and monitored. Important tactics consist of: the building sector is accountable for almost 1/3 of the world's resource consumption, as are the materials it consumes. This has a big impact on degrading ecosystems and carbon emissions. One efficient strategy to lower the built environment's resource consumption and carbon intensity is to reuse and recycle construction materials. Reusing materials in new construction was formerly commonplace, but it's now the exception rather than the rule. When recycled or reused materials are used, it's typically on a small scale that falls short of what's required to have a significant influence on climate change. Reused materials aren't used more frequently for a variety of reasons. One is the imbalance between the demand and supply for recyclable and reusable materials. This implies that future projects cannot depend on the availability of recycled or repurposed materials, which may cause schedule delays. There cannot be a large-scale demand for materials if there is a restricted or irregular supply. In the creative initiative Die Musterbud, A tiny cabin is built from 7 different kinds of reclaimed concrete. Although recycled concrete has been in use for many years, this experiment compared it to conventional concrete by utilizing innovative mixes that included recycled sand and trash from demolished buildings. The project's goal was to evaluate the recycled concrete mixture's technical and environmental aspects in comparison to a conventional concrete mixture made with fresh aggregates. The Musterbud's main building material is recycled concrete, which is produced by crushing and reusing extra concrete from buildings that have been demolished. The project enables a deeper comprehension of the practical performance of recycled concrete as well as its possible advantages in terms of material circularity and sustainability. The project makes a strong case for sustainable building methods that promote the circular economy in the construction industry by showcasing the effective use of recycled concrete aggregates. Anonymous, 2024, Figure 9 Urban Mining in Action, Examples of Material Reuse and Recycling. Sustainable disposal practices. When recycling or reuse is not an option, environmentally friendly disposal techniques ought to be adopted. The process of treating and reusing wastewater from sources other than toilets, like sinks, showers, and washing machines, is known as gray water recycling. Black water is a more seriously contaminated wastewater from kitchen sinks and toilets than gray water. Polluted wastewater from kitchen sinks and toilets. Gray water can be cleaned and put to use for flushing toilets and other non-potable uses like irrigation. There are 3 categories for gray water recycling systems: membrane systems, biological systems, and disinfection systems. Using chemicals, UV light, or other techniques, filtration and disinfection are frequently used to remove solids and contaminants. Reusing gray water offers various benefits, such as lowering wastewater production and water consumption, which can preserve water resources and lessen the strain on municipal water treatment facilities. Rainwater harvesting is the process of gathering and preserving rainwater for use at a later time. Rainwater harvesting is the process of collecting rainwater before it enters the municipal stormwater system or groundwater, as opposed to gray water recycling, which involves treating wastewater. Rooftop catchment systems, surface runoff systems, and subsurface storage systems are the 3 categories of rainwater harvesting systems. Rainwater collected can be utilized for non-potable uses including laundry, toilet flushing, and irrigation if it is handled properly. Rainwater harvesting has a number of benefits, such as lessening the demand on municipal water supplies, particularly in dry or scarce periods, and lowering stormwater runoff, which can lessen erosion and flooding. It can also be utilized for irrigation, which lessens the need for drinking water. Potential drawbacks or restrictions include the need for regular maintenance to prevent pollution and any legal or regulatory issues pertaining to water rights and water quality standards. In general, rainwater collecting is an economical and environmentally friendly way to save water, especially in arid or costly areas. The primary distinctions between rainwater collecting and gray water recycling are that they are both effective ways to reuse water and reduce the demand on municipal water supplies. However, there are a number of noteworthy differences between the 2 approaches that could affect how well they work in certain situations. Gray water may contain contaminants like soap, detergents, and bacteria, which results in a lesser quality than rainwater. While rainfall can typically be used without treatment for non-potable uses, gray water requires more extensive treatment before it can be reused. When it comes to rainwater harvesting, local rainfall patterns and roof size are often more important factors than gray water recycling, which is determined by the amount of wastewater a family produces. However, rainwater collecting can provide more water than gray water recycling during periods of heavy rainfall. Things to think about: the choice between rainwater harvesting and gray water recycling will depend on a number of factors, including the local temperature and rainfall patterns, the availability of water resources, and municipal legislation governing the use of reclaimed water. Homeowners and companies should carefully consider these problems before deciding which technique to employ. Generally speaking, rainwater collecting and gray water recycling are both great ways to reduce water use and conserve water resources, the best course of action will depend on the needs and circumstances of the individual user. Anonymous, 2024, through the use of these tactics and procedures, the building sector may greatly cut waste, encourage recycling, and help create a more sustainable future. In addition to being good for the environment, the emphasis on waste management promotes a culture of accountability within the industry. Chapter 9 Climate Responsive Architecture. Climate responsive architecture is a design methodology that optimizes building comfort, energy efficiency, and sustainability by taking into account the local climate and environmental variables. This chapter covers a variety of passive design tactics, thermal mass, building orientation, insulation methods, and extreme weather event considerations. Passive design strategies for different climates using natural resources as efficiently as possible to keep indoor temperatures comfortable is known as passive design. Building orientation and shape. The goal of passive design techniques is to achieve thermal comfort with the least amount of active heating and cooling. This entails using proper orientation, external shading, the right quantity of glazing, and natural ventilation to reduce the need for heating in the winter and cooling in the summer. Sustainable architecture practices require filtered, indirect, glare-free daylighting to drastically reduce, if not completely eliminate, the requirement for artificial lighting. In addition to lowering energy use for air conditioning and lighting, daylighting improves occupant health and happiness. The building's skin, which consists of the roof, windows, and walls, mitigates the effects of the weather. Choosing a building envelope that meets the needs of the building in terms of insulation, thermal mass, and color can cut down on the amount of time that heating or cooling is needed to keep people comfortable. It is possible to further minimize the need for air conditioning by utilizing evaporative cooling techniques such as evaporative coolers and water bodies, particularly in the hot and dry months. Evaporative cooling can now be easily included into traditional air conditioning systems. In India, ceiling fans are a common fixture in homes and are frequently the only source of cooling during the summer. These days, they are also making a well-earned resurgence in commercial structures. Ceiling fans are a common feature of modern, energy-efficient buildings. They improve thermal comfort and lower cooling energy use. Anonymous, 2024, Thermal mass and insulation techniques. Two essential elements of passive design that aid in temperature regulation are thermal mass and insulation. The ability of a substance to absorb, hold, and release heat is referred to as its thermal mass. Large thermal mass materials, such as concrete and water, are characterized by their large heat storage capacities. Low thermal mass refers to the extremely limited heat storage capability of insulation foam. Thermal mass is frequently compared to a type of thermal battery. The battery charges up to the point where it is fully charged when heat is applied, up to a certain extent, by radiation or warmer surrounding air. When heat begins to escape as the nearby airspace gets noticeably colder, it discharges. Although thermal mass has always been a feature of buildings, it has only recently developed into a tool for energy conservation. The manufacturers of high thermal mass materials particularly latched upon the 2005 ERUPS report UK Housing and Climate Change as the rationale behind heavyweight construction. ERUPS depicted the rising temperatures throughout the United Kingdom and contended that the Mediterranean climate of the future warranted the use of heavyweight architecture. ERUPS were partially correct. Both masonry and timber frame construction types can accommodate thermal mass, but the more nuanced message about thermal mass has remained hidden due to the manufacturing sector's quick appropriation of the report and its subsequent pervasiveness. Realizing the advantages and possible drawbacks of thermal mass requires an understanding of its characteristics and application, especially in context. A material's capacity to both absorb and release heat from a space as the interior temperature fluctuates over time is measured by its thermal admittance. When evaluating heat fluxes into and out of thermal storage, admittance values can be a helpful tool in the early phases of design. In ISO 13786:2007, thermal admittance is completely described. The SIBS Simple Dynamic Model, SIBS, 2005, Guide A, Environmental Design, for computing cooling loads and summertime space temperatures is similarly based on the framework that is provided. Figure 10. The effectiveness of some common materials. The operation of thermal mass. High thermal mass smooths out the extremes in daytime temperatures by alternating between storing and releasing heat. Heat is absorbed during the day and released in the evening in warm/hot climates where there is a noticeable difference in temperature between day and night, known as diurnal variation. The extra heat can either be flushed out through natural ventilation or used to heat the space when the outside temperature drops. The next day, the entire procedure might be carried out again. Figure 11. Summer cooling. Figure 12. Winter heating. It's not necessary for the heating and cooling pattern to follow the daily changes in temperature. For instance, thermal mass can be built to absorb heat produced by office equipment, lights, and people when they are not using the area, and then release it when they leave. This can be done in places like workplaces or schools where there is a pattern of human activity. Finding the thermal mass. Thermal mass must be protected from the effects of outside air temperatures and exposed, or coupled, to the heated interior area. The mass is placed inside the insulated building envelope to accomplish this. The thermal mass can be any heavy material. It might be a component of the ceiling, walls, or floor of the interior. Thermal mass may absorb heat without being exposed to direct sunlight, even though this is frequently desired. Convection and radiation are two ways that heat can move between surfaces. Learn more about physics of buildings, heat transfer, conduction, convection, and radiation. More insulation materials, thermal properties. More U value for dummies. More air tightness. More air barrier design. More thermal bypass. More decrement delay and thermal buffering. More thermal mass. More patience. 2024. Architects may design buildings that not only satisfy the demands of their occupants but also effectively address the current climate issues by using these climate-responsive solutions. This promotes sustainability and resilience in the built environment. Designing for extreme weather events. The frequency and intensity of extreme weather events including hurricanes, floods, and heat waves have increased due to climate change. Resilient designs that can survive the effects of these natural disasters are necessary when building for such occurrences. Using a variety of elements and techniques, resilient building design increases a structure's capacity to withstand harsh weather. Strategically placed to reduce the chance of flooding or landslides, while simultaneously utilizing natural elements like shadow and the direction of the wind to increase their resistance to harsh weather. All things considered, designing buildings that are resilient to the effects of climate change and extreme weather is essential. We may contribute to the creation of a built environment that is more resilient and sustainable by including these elements and techniques into building design. Building for climate change requires a strong sense of community. Building resilient communities is a key component in mitigating the effects of extreme weather and other climate-related issues. A mix of physical, social, and economic interventions that improve communities' capacity for shock and stress adaptation and recovery is what is meant by community resilience. Creating and executing effective resilience plans require community engagement. Results from participatory approaches that include community people in decision-making processes can be more long-lasting and productive. Additionally, it fosters a sense of ownership and trust among community members, both of which are essential for the long-term success of resilience initiatives. Tactics. Creating and executing effective resilience plans require community engagement. Results from participatory approaches that include community people in decision-making processes can be more long-lasting and productive. Additionally, it fosters a sense of responsibility and trust among community members, all of which are essential for resilience's long-term effectiveness. Policy and regulations role. One of the main forces behind the promotion of resilient design for climate change is effective policy and regulation. Building regulations and policies related to climate change can offer a foundation for developing resilient and sustainable built environments. These regulations can encourage the use of cutting-edge materials and technologies and set performance requirements for infrastructure and buildings. Resilience measures like installing backup power sources or using materials resistant to flooding may also be mandated by building codes. Governments can facilitate the adoption of resilient design approaches by enacting laws and regulations in an efficient manner. Another effective strategy for enticing the business sector to invest in resilience is regulation. Green bonds, for instance, can be used to fund resilience initiatives, giving investors a means to both financially benefit from and support sustainable projects. It is noteworthy that extensive rules and regulations pertaining to climate change are imperative in order to guarantee the extensive implementation of resilience measures. A less resilient built environment could arise from stakeholders having less incentive to invest in resilience in the absence of strong policies and regulations. Henry, 2024, Figure 13 Built Environment Chapter 10, Urban Planning and Environmental Impact. The physical attributes of built environments, such as building density, infrastructure layout, and patterns of land use, are referred to as urban form. Urban form and environment have a complicated and nuanced interplay. 10.1 Relationship between urban form and environment. Urbanization will sacrifice a portion of the natural environment in terms of spatial distribution, which will lead to an uneven degree of coordination in the new area. However, this will gradually improve with future ecological engineering and other interventions. Because to their early construction, several urban districts in the JRB have poor ecological environment quality. Nonetheless, as cities continue to grow, the natural environment is artificially improved, the urban environment is made more beautiful, the vegetation cover is increased, and the interaction between the natural and built environments is strengthened. Investigating the connection between urbanization and ecology, an analysis was conducted using a multiple linear regression model of CCD with RSEI and NTL to examine the relationship of coupling between watershed ecology and urbanization. The interplay between urbanization and the natural environment in an offshore watershed offered guidance for future peaceful coexistence of nature and humanity in China at the watershed scale. First, there was a connection between urbanization and the natural environment. Future studies might therefore concentrate on the mechanisms and course of urban growth and expansion as they relate to the biological environment at the watershed scale. The indices of the ecological environment and urbanization are calculated in a biased manner. For instance, the assessment should be heavily influenced by factors like land use intensity, population density, and air quality. This work uses the RSEI to determine the link coordination relationship between urban growth and the biological environment in the JRB by building the CCDM based on NTL and Landsat remote sensing data collected between 2000 and 2020. One can infer the principal findings listed below. 1. Between 2000 and 2020, there was an increase in JRB urbanization level and a mean NTL increase from 0.1 to 1.15. Nonetheless, most counties' degrees of urbanization improved gradually, with notable variations amongst them. 2. The JRB's mean RSEI was continuously higher than 0.6 during this time, indicating a high-quality ecological environment. The combination of human activity and climatic variables contributed to the low RSEI score in 2005. During that time, the basin had a rise in temperature and a fall in precipitation, which decreased the moisture content of the surface soil. This had an impact on the growth of vegetation, lowering the RSEI and the ecological environment's quality. 3. During the 2000 to 2020 decade, the JRB's coordination category between urbanization and the ecological environment was mostly basic coordination, and the percentage of places that were imbalanced rose. Furthermore, it was discovered that better coordination occurs in counties with higher levels of urban development. 4. Increasing urbanization has a greater positive impact on regional coupling coordination than does improving the quality of the ecological environment. However, in order to prevent reducing development coordination, it is imperative to give greater consideration to maintaining the ecological environment when increasing urbanization, given the antagonistic relationship between urbanization and the environment. Lewin, 2023, in certain cases, urban planning can promote a balance between growth and environmental preservation by coordinating urban expansion with ecological sustainability. Sustainable urban mobility. A sustainable urban mobility plan is a strategy plan created to meet the demands of businesses and individuals for mobility in urban areas in order to improve the quality of life. It expands upon current planning procedures and gives integration, participation, and assessment principles appropriate weight. A SUMP should consider actual traffic patterns and encompass the whole functional urban area, which includes a city and its commuter zone. A SUMP should anticipate collaboration and synergies among all governmental levels, local, regional, and federal, as well as between various policy domains. It ought to be prepared in collaboration with stakeholders and locals. It guarantees a range of environmentally friendly mobility choices for the smooth, safe, and healthy movement of people and commodities while taking into account the needs of other city dwellers and the urban environment. SUMP principles and concept. The Commission unveiled a proposal for sustainable urban mobility planning as part of the 2013 Urban Mobility Package. Numerous European cities and towns responded favorably to this, spurring the creation and revision of hundreds of urban mobility plans. Enable towns and cities to create an SUMP. The European Commission keeps spreading awareness through networking opportunities, training sessions, and examples of best practices. Additionally, it offers financial opportunities and a platform for project coordination for SUMP-related initiatives. All cities have access to a compilation of non-binding guidelines and reference materials created through CO-funded projects by the EU to assist them in creating and implementing their own SUMPs. Cities are welcome to use these informational resources as they see fit for their own need. Hoekstra, 2024. Urban planning that integrates sustainable mobility concepts can improve community health and lessen the consequences of climate change. 10.3 Green spaces and urban biodiversity. Urban environments need green spaces because they have a direct impact on residents' well-being and the health of the environment. Public areas found in urbanized areas typically have poor biodiversity, and urban green spaces are known to have limited capacity to support biodiversity. However, there is a chance to enhance these traits with affordable and easily applied restoration treatments. The objective of this study was to increase the local biodiversity in 3 urban parks located in Sorocaba, SP, Brazil, by implementing a series of nature-based interventions. The goal of our actions was to promote regional ecological succession. We created 9 sample units, SU, in each park by taking out grass in circles with a diameter of 1 meter each. 3 SUS in each park were left uncovered, control treatment, for the duration of the trial. 3 received a transposition treatment, forest litter gathered in a nearby, well-conserved forest fragment, and 3 SUS had a perch erected, perch treatment. After the treatment was established, we observed each SU every 2 weeks for a year, noting the quantity and kind of seedlings that emerged in the circles. We saw variations in the number of seedlings in each of the 3 parks' experimental treatments, which suggests that species survival rates vary. 30 genera in all were identified by us, the majority of which were native herbaceous plants. Regarding the seed dispersion syndrome group, the majority of seedlings belonged to species that were spread by abiochoric vectors. The most prevalent botanical family was Asteraceae. While it is true that the experimental methods we investigated may not have produced the desired number of shrub and tree species, these treatments were also safe because they did not lead to the domination of foreign species. We conclude that because of this approach's ease of elaboration and implementation, respect for the natural structure and functioning of urban green spaces, and potential for success, Castelli, 2021, invigorated urban communities and robust ecological networks are 2 benefits of carefully planned green spaces to enhance urban biodiversity. 10.4 Managing urban heat islands. Urban heat islands, UHIs, are parts of cities where the temperature is noticeably higher than in the surrounding rural areas. The widespread use of concrete and asphalt, as well as industrial operations, are the main causes of the issue. To lessen the impact of the heat island effect and increase your community's ability to withstand heat waves, use the advice below. Make your home more shaded by offering shade and facilitating cooling through evapotranspiration. Planting trees and other vegetation decreases air and surface temperatures. Your home will become more pleasant and require less air conditioning if trees and other plants directly shade it, which will also lower your energy costs. In addition to enhancing air quality and offering comfortable shade for outdoor activities, trees also shield your family's health from dangerous UV rays. Put in green roofing. A vegetative layer cultivated on a rooftop is referred to as a rooftop garden or green roof. In addition to providing shade, green roofs lower air temperatures by removing heat from the atmosphere through evapotranspiration. Green roofs serve as insulators for your house, absorbing heat, and lowering the amount of energy required for heating and cooling, thereby cutting your energy costs, increasing indoor comfort, and lessening the stress that comes with heat waves. Put in cool roofs. In order to lower roof temperatures, cool, or reflective, roofs aid in reflecting heat from the sun and away from your house. As a result, you can keep your house cooler and use less air conditioning on hot days. A Californian study, 1, found that cool roofs can save approximately 50 cents per square foot on energy costs annually. These energy-saving measures can also lead to reduced greenhouse gas emissions into the environment and improved local air quality. Make use of energy-saving devices and appliances. By making use of energy-efficient equipment and appliances in your house, you may lessen the strain on the electrical system during heat waves and guarantee a more consistent supply of electricity for your neighborhood. To help you choose the most energy-efficient option, seek for the EPA's Energy Star label on products you purchase. More than 60 product categories, such as appliances, lighting, electronics, office supplies, heating and cooling equipment, and lighting, have the Energy Star label. You can also save money by swapping out your outdated appliances and equipment for Energy Star qualified goods. Reagan, 2024, cities can improve the quality of life for their residents and increase their resistance to climate change by identifying and mitigating urban heat islands. The significance of incorporating environmental factors into urban planning techniques is emphasized in this chapter. Ecosystems, public health, and general urban livability can all be strongly impacted by the sustainable management of urban surroundings. Case studies in sustainable building. Notable green buildings from around the world. The America's Greenest Buildings. 1. Benjamin Romano's Torre Reforma in Mexico City. Figure 14. Torre Reforma by Benjamin Romano, Mexico City, Mexico. With a height of 246 meters, the Torre Reforma is currently the fourth tallest structure in Mexico and commands a commanding view over one of the megalopolis's main thoroughfares. Only projects with exceptionally effective resource management are granted the LEED Platinum certification, which was granted to this tower in 2016 atop a colonial-era building. Notable accomplishments of this project include, 100% of wastewater is processed to tertiary levels and utilized within the building, 94% of the areas have natural illumination, and the concrete walls that serve as the building's foundations limit heat entry, saving up to 20% on energy usage. In addition, the building is close to additional amenities and metro lines by foot. 2. Perkins and Will's Albion District Library in Toronto, Canada. Figure 15. Albion District Library by Perkins and Will, Toronto, Canada. Situated in Toronto, this sanctuary for newly arrived immigrants has successfully enhanced the local community by offering a landmark location for educational and recreational purposes. A sloping green roof, built-in photovoltaic arrays, native tree species, bike infrastructure, and the building of a wetland to collect runoff for irrigation are some of the characteristics of the library. Without compromising comfort, the building was able to lower its overall energy use by 40% when compared to the national average. 3. Plus Arquitectos Transocean building in Santiago, Chile. Figure 16. Transocean building by and Arquitectos, Santiago de Chile, Chile. The design of this office building placed a lot of emphasis on creating a shape that maximizes its orientation, giving natural light top priority, making sure that every area has views of the outside, and carefully treating the facade to prevent unintended heat gains or losses. Modern domotic technology avoids using artificial lighting when it's not needed by adjusting lights within the building based on the amount of sunlight outside. Because of its exceptional energy efficiency, which allows it to save up to 70% on energy expenses. The building became the first in Chile to receive the LEED Gold certification. African Green Buildings 4, Cornell Adeyemi's Floating School in Lagos, Nigeria. Figure 17 Floating School by Cornell Adeyemi, Lagos, Nigeria. The architect Cornell Adeyemi devised an alternative to the conventional school system in order to address the primary difficulty of providing education for a community living in a flood-prone city that feels highly threatened by the increasing sea levels. Constructed with bamboo, locally available timber, and 256 plastic buoys fashioned from barrels, this project goes beyond a sustainable structural solution. Other tactics employ cutting-edge technology, such as rainwater collection devices to aid in sanitation and solar panels to generate electricity. This project is a great example of how to address current issues by combining traditional and new methods. When it opened in 2015, this school has been serving 100 kids from all across the region. But in June 2016, the building fell as a result of intense rain. The project's design has won numerous accolades, including 2014's Design of the Year. There were two further design modifications in 2016 and 2018, which improved the school's general layout and structural soundness. 5 Innovative Joe Osiado's House in Accra, Ghana. Figure 18 Innovative Home by Joe Osiado, Accra, Ghana. In remembrance of his family, this house was constructed with local resources including wood, mud, and timber, minimizing the need to carry supplies from outside the city or other locations and lowering overall carbon emissions. In order to accommodate underfloor cooling, the structure is raised 3 feet off the ground on a wooden deck, adhering to the no air conditioning principle. Excellent cross ventilation is made possible by wood screens and louver-like panels on floor-to-ceiling windows, which eliminates the need for artificial climate control systems. A great example of bringing traditional customs into the present day. 6. McPierce and Arup Associates, Eastgate Center, Harare, Zimbabwe. Figure 19 Eastgate Center by McPierce and Arup Associates, Harare, Zimbabwe. The self-cooling termite mounds in Africa and native masonry served as inspiration for the creative design of the Eastgate Center. Passive architecture and energy-efficient techniques are used in this structure to regulate the climate. Because of the high thermal capacity of the building materials used in its construction, this sustainable green structure can store and release heat obtained from its surroundings. The plants in the facade and the clay lattice also contribute to the reduction of heat received. Integrated fan systems are available that operate on a cycle designed to enhance heat retention during the hot day and release heat during the cool night. These architectural features lessen the amount that the interior of the building changes in temperature as the outside does. The building's temperature is maintained year-round without the need for traditional heating or cooling, which lowers electricity costs and creates a passive cooling system without compromising occupant comfort. Asia's Green 7. Gensler's Shanghai Tower in Shanghai, China. Construction. Figure 20 Shanghai Tower by Gensler, Shanghai, China. The financial center of Shanghai, a busy city, is home to the second tallest building in the world. The structure is designed with a revolving series of double-skin cylinders arranged one over the other to create a dynamic curving shape that efficiently reduces wind loads by 24%. Enough light and insulation are provided by the building's double skin, which also lowers the energy required for the tower's heating and cooling. One of China's most ecological skyscrapers, the Shanghai Tower earned a Platinum LEED certification in 2016 thanks to energy-saving measures that save $556,000 a year. 8. Asia Square by Denton Corker Marshall, Singapore. Figure 21 Asia Square by Denton Corker Marshall, Singapore. Denton Corker Marshall built Asia Square using sustainable design principles from the start. This skyscraper has been recognized as one of Singapore's greenest structures since it opened in 2011. In comparison with other commercial buildings, Asia Square uses 35% less energy. The oil collected from tenants' eateries is used by an on-site biodiesel plant to produce power. Additionally, the lift's generated kinetic energy is transformed back into electrical energy and dispersed throughout the system. Additionally, Water and vapor droplets are gathered from the air handling devices and applied to the green spaces for irrigation. 9. Nihon Sekkei Inc.'s Tokyo Toranomon Global Square, located in Tokyo, Japan. Figure 22. Tokyo Toranomon Global Square by Nihon Sekkei Inc., Tokyo, Japan. The office floors of the building were equipped with separate sensitive and latent heat air conditioning systems, which was one of the tactics used by the building's designers to drastically reduce the amount of air conditioning used. All sections have a 30% increase in natural ventilation, and energy savings are considered through the use of free cooling depending on the outside weather and the control of CO2 demand. The project building's energy expenses were lowered by 30.3%, as demonstrated by the energy optimization techniques indicated above. The project building's performance in energy regulation earned it the highest rank 3 in the Tokyo Green Building Program Indiana Edition to Elite Gold certification. The installation of motion sensor and auto-dimming lighting control systems, the reuse of rainwater, the installation of energy-efficient LED lighting fixtures throughout the building, and the reduction of lighting power in empty spaces are a few examples of reviewed activities. Europe's Green 10, Benisch Architekten's Marco Polo Tower in Hamburg, Germany. Building Figure 23. Marco Polo Tower by Benisch Architekten, Hamburg, Germany. The 55-meter tall tower, which is based on providing luxurious living quarters and an all-encompassing sustainable green building design, is a unique and spectacular sculpture that acts as a lighthouse for the promenade on Strandkai and the neighboring cruise ship terminal. Because of the overhanging terraces above, which shield the recessed facades from the sun's direct rays, additional sunshades are not necessary. This building uses techniques like heat exchangers and vacuum collectors on the roof to convert heat into cooling for the flats. Natural ventilation is permitted in the sleeping areas thanks to creative sound-insulated air louvres, which also reduce external noise pollution. 11. Bjarke Ingels Group's Copenhill in Copenhagen, Denmark. Figure 24. Copenhill by Bjarke Ingels Group, Copenhagen, Denmark. At one point, the massive project, which had a 3.5 billion Danish kroner budget, was Denmark's largest environmental undertaking. When it was built, it established a standard for context integration and community interaction. The 41,000 square meters plan includes an urban entertainment complex and an environmental education center that draw people in and turn the infrastructure into an architectural landmark for the city. Beneath the sloping roof, furnaces, steam, and turbines convert 440,000 tons of waste every year into clean energy, enough to power and heat 150,000 houses. Copenhill is a continuous facade made of 1.2 m height by 3.3 m broad aluminium bricks placed like giant bricks overlapping each other. 12. PLP Architectures The Edge in Amsterdam, the Netherlands. Figure 25. The Edge by PLP Architecture, Amsterdam, the Netherlands. The Edge, an office block with the highest BREEAM rating in the Netherlands, is a benchmark for sustainability initiatives. Located in Amsterdam's Zeewittes commercial sector, this 40,000 square meters office building was constructed for the multinational financial firm Deloitte. To build flexible and intelligent workspaces, it integrates a variety of smart technologies, some of which are listed below, with the most solar panels of any office building in Europe. A plethora of solar panels are integrated into the roof and the south-facing exterior. An aquifer thermal energy storage system provides all of the energy needed for heating and cooling. An aquifer thermal energy storage system provides all of the energy needed for heating and cooling. A Philips design system individually controls each luminaire in the building, resulting in a 50% reduction in energy consumption over TL5 lighting. Unique facades that capitalize on their orientation through the use of passive design. Every facade adapts its design to the amount of sunshine it receives, whether it means adding solar panels, utilizing louvres to create shade, or using thicker glass to reduce outside noise. The Edge uses 70% less electricity than other office buildings thanks to these techniques. This building was certified by BREEAM to evaluate the most creative features of its design and construction. The building's overarching goal has always been to be a model of excellence, to distinguish itself as a forward-thinking workplace that sets the bar both nationally and globally. Oceania and the Pacific, Green Buildings 13. Decibel Architecture's Pixel Building in Melbourne, Australia. Figure 26 Pixel Building by Decibel Architecture, Melbourne, Australia. The Pixel Skyscraper, Australia's first carbon-neutral office skyscraper, became a city landmark with its innovative design that stretched the envelope of what was conceivable for a green building and its eye-catching facade of rainbow panels. Among the new sustainable building technologies that were used were Hoover toilets, solar and wind power, thermal cooling, anaerobic digestion of toilet waste, and pixelcrete, a specially designed concrete that has half the embodied carbon of conventional concrete for the same structural properties. Due to its efficient use of resources and energy, this project received 105 LEED and 105 Green Star points. 14. Parc Architects French Polynesia Cultural Center located in Papeete, French Polynesia. Figure 27 French Polynesia Cultural Center by Parc Architects, Papeete, French Polynesia. The first significant cultural center in Polynesia will be the Polynesian Cultural Center in Papeete. It is made up of several areas for cultural events, including galleries, an art center, a media library, an auditorium, reading rooms, workshops, a coffee shop, a store, and offices that honor the area's traditional culture. Large, light-filled patios with native plants that provide views and lighting are the focal point of each location. Rain is collected by the building's bird-like roofs, which also enable integration with the local environment, negating the need for artificial climate systems across the entire structure. By the year 2024, the building's construction is anticipated to be completed. 15 Zan's International House in Sydney, Australia. Figure 28 International House by Zan's, Sydney, Australia. The largest commercial office building in the world, International House is 7 floors tall and uses mass-engineered timber as its main structural component. Approximately 3,500 cubic meters of repurposed and sustainably farmed wood were used in the construction. By not utilizing concrete, thousands of tons of greenhouse gases were prevented. Softwood is used for interior design and hardwood for external structural purposes. Via the use of recycled hardwood and structurally engineered mass timber, the design makes the most of their limits to produce a visually striking and comprehensible load path via the column and beam construction. Prefabrication of the structure allowed for additional quality control through off-site factory manufacturing and a significant reduction in construction time. Before procurement, all penetrations, connections, and interfaces were coordinated using a thorough 3D digital documentation process, which allowed the timber components to be fully prefabricated. One example of placemaking architecture that reduces adverse environmental effects in the built environment is International House Sydney. It acts as a lighthouse for plans aiming at the global future of commercial building construction. Modern solutions are necessary for modern problems. Many people agree with this sentiment, particularly when talking about the inventions that will be employed to solve the issues brought on by climate change. But as this list shows, utilizing both conventional and modern building techniques, sustainable architecture may significantly lower CO2 emissions and enhance energy savings. In order to go forward and confront the issues that sea level rise and global warming will bring to our cities, architects will need to start looking to the past for inspiration. Jacques, 2020, Lessons Learned from Successful Projects. There are numerous reasons to carry out a lessons learned procedure. The following list of the 12 most popular ones is provided, recognizing and steering clear of any hazards and errors. By avoiding the same mistakes in future projects, the process helps the project team identify and address difficulties and mistakes made throughout the project. Enhanced teamwork and communication, including all relevant parties in the process, will foster better teamwork and communication within the project. Enhanced productivity, by comprehending and rectifying the obstacles and errors encountered in the ongoing project, the methodology can facilitate and augment productivity for all subsequent undertakings. Enhanced overall project performance and results, by recognizing and resolving obstacles and errors encountered during the project, the project team can enhance overall project performance and results. Finding best practices, provides a chance to find best practices that can be applied to and adhered to in subsequent projects. Finding opportunities for improvement, the project teams are able to pinpoint project and process areas that require enhancement, which they can then use to assist with subsequent projects. Enhancing reference materials and project documentation. Preparing a well-written report and document with comprehensive information can be a useful resource for the facilities department to refer to in the future when the facility is being operated. Improved educational experience. The project as a whole can engage in giving and receiving feedback and input from many various viewpoints by incorporating all team members in the process, which improves the learning experience. Improving project documentation and reference materials. When the facility is being operated in the future, the facilities department may find it helpful to have a well-written report and document with extensive information. Enhanced quality of the educational experience. By involving every team member in the process, the project as a whole can participate in providing and receiving feedback and input from a wide range of viewpoints, which enhances the learning experience. Increased creative potential. If the process is carried out properly, it will motivate the group to reflect critically on their work and come up with fresh ideas. Increased possibility of cost reduction. The team can generate larger potential cost reductions for future projects by addressing obstacles and any mistakes/issues made during the project. Morris, 2023, Challenges faced and solutions implemented. Obstacles in the way of sustainable development. We face numerous challenges that could obstruct our progress as we work to create a world that meets current demands without endangering the ability of future generations to meet their own. Our environment is deteriorating, and social injustices continue to exist. These problems put our resolve to the test and need creative answers. 1. Overuse of resources and deterioration of the environment. The ecosystem is strained by unsustainable production and consumption methods, which lead to pollution, habitat loss, deforestation, and resource depletion. Promoting sustainable development requires tackling excessive consumption and adopting sustainable resource management techniques. Reaching this means working together across sectors and societal levels to maximize resource efficiency, reduce waste, and switch to renewable energy sources. 2. Urbanization and population growth. The world's population is still growing, and many places are seeing fast urbanization in tandem with it. This pattern puts a strain on services, infrastructure, and resources, resulting in problems like overcrowding, poor housing, congested roads, and increased energy use. In order to address these problems and promote the development of livable and resilient cities, it is necessary to give priority to inclusive development and sustainable urban design. 3. Of poverty. Spatial divide. Sustainable development initiatives are significantly hampered by poverty and inequality. Millions of people around the world are impoverished and do not have access to basic essentials. Beyond only material prosperity, this deprivation stifles prospects for both economic and personal progress. Therefore, within frameworks of sustainable development, reducing poverty and social inequality is essential to fostering social cohesiveness, economic growth, and environmental preservation. 4. Climate change. Its consequences. Climate change, which is characterized by high temperatures, harsh weather, rising sea levels, and disturbance of ecosystems, poses significant hazards to ecosystems, communities, and economies. Reducing greenhouse gas emissions, adjusting to the effects of climate change, and building a low-carbon, climate-resilient society are essential actions to guarantee sustainable development in the face of this worldwide crisis. 5. Insufficient availability of essential human needs. Initiatives for sustainable development face a major obstacle due to limited availability to basic human needs. Millions of people throughout the world lack access to basic necessities including clean water, sanitary conditions, medical treatment, and education, which lowers their quality of life and limits their ability to have a positive impact on society. In order to promote social justice, well-being, and equity, it is essential for sustainable development to attend to these fundamental requirements. Through guaranteeing that everyone has access to the necessities of life, communities may foster a prosperous and inclusive future in which every person can live a life that is both respectable and meaningful. In conclusion, governments, corporations, civil society organizations, and individuals must work together to create and implement sustainable solutions that put the welfare of people and the environment first in order to address these issues. You can read more about the UNDP's assessment of the obstacles to sustainable development and the ways in which the global community is assisting by clicking this link. Santiago Rodriguez, 2024. In summary, there are many advantages to sustainable building practices, but there are also big obstacles to overcome. We can design spaces that not only benefit the environment but also improve the lives of those who inhabit them by using best practices and the lessons we can learn from case studies that have already been completed. Chapter 11, Future Directions in Building and Environmental Design. Innovative Technologies in Building. 8 Novel Technologies for Construction. Virtual and augmented reality. Construction technology has advanced significantly with the use of virtual and augmented reality, which provides visualizations. The industry is predicted to grow by $8 trillion globally by 2030, thus the use of VR and AR will surely be significant. Several remote site inspections have noted the presence of AR/VR technology, and it has been proposed that building costs might be cut by 90% by 2022 if used. It also makes it easier for AEC employees to collaborate, communicate, and stay safe. UAVs. For more than 10 years, construction has been using drones. Drones with an AI focus should become increasingly advanced by 2023 and beyond. Drones using 3D LiDAR scans and real-time aerial imagery are revolutionizing construction processes. Anticipate increased compatibility with drones operating in scan-to-BIM mode, which shares construction data with other BIM-based platforms in a matter of microseconds. Blockchain methods. The AEC sector as a whole will have more effective cost control and blockchain-based procurement methods by 2023 and beyond. This technology, which functions as connected collections of data blocks that comprise a digital ledger with the records of all transactions and accomplished milestones, was first introduced to the construction sector less than 10 years ago. It resembles a real chain, where each link signifies a different project transaction, and it self-corrects automatically. It is safe, decentralized, and flexible enough for projects of any scale, in contrast to others. Digital replica. The newest technology in the AEC sector, the digital twin, solves problems with operation management. It entails modeling in order to design a building prototype. Intelligent multidimensional digital models are used in digital twin trends and functioning. Buildings experiencing operational problems will become less common by 2023 and beyond because digital twins can mimic, forecast, and provide information for decisions based on actual conditions. With the use of patterns and spatial arrangements, digital twins do performance analysis while taking occupant behavior into account. Scanner with 3D laser. The 3D laser scanner is one of the newest tools for construction in the AEC sector. It is constantly a new innovation because of its interoperability and annual changes. It is renowned for its capacity to examine and evaluate actual objects. It has been used for many different construction jobs, including safety, project inspection, mapping, and on-site surveying. Because of its accuracy, building planning is simple and significantly less expensive. Utilization case. The French hospital Aiguilles-Cures Hospital Center, situated in the French Alps, is one example of a practical deployment of this technology. Using ScanBIM and a 3D laser scanner brand called Faro, ATFF was able to capture every aspect of the current hospital and create a new model for renovations. 4D modeling. 4D simulations are one of the newest technological options to save time and money for both onshore and off-site projects, as the construction industry is always looking for ways to optimize processes. Utilization case. By using 4D simulation, the Bentley pipeline project for the Haweswater Aqueduct by Mott MacDonald saved 20 days. Constructing information models. Another rapidly emerging cutting-edge technology in global construction is BIM. it is an essential tool for contemporary engineering, building, and architectural processes. This technique enables the production of one or more accurate digital models of buildings with good interoperability. This novel technology, which has applications to projects of all sizes and levels, is supported by the officially recognized ISO 19650 standard. In 2022, BIM software such as Revit, Navisworks, Tekla, BIM Collab, Plannerly, and Autodesk BIM 360 will provide interoperability. The 3D printing process in the construction sector. 3D printing is one of the newest technologies, however not as popular as BIM. Its method was originally applied in 1995 and involves creating three-dimensional buildings from computer models. In 2023, using 3D software to create 3D models is a popular trend. Use cases: Arup engineers created the steel nodes for a lightweight structure using 3D printing. Furthermore, the Shanghai-based company Winsun Decoration Design Engineering used 3D printing to spray a blend of recycled raw materials and quick-drying cement. Anonymous, 2023, the role of policy in sustainable development. In order to promote sustainable building practices, policies are essential. Green buildings are essential to sustainable development because they use less energy, have a less environmental impact, and improve the health and well-being of its occupants. This review emphasizes the significance of government intervention in advancing sustainable building practices as it examines the role of policy and regulation in promoting green buildings. Government rules and policies have a significant influence on how green building techniques are adopted. Governments can promote the development and restoration of buildings that prioritize environmental sustainability, water conservation, and energy efficiency by enacting laws, offering incentives, and setting standards. One of the best instruments available to governments for promoting green buildings is the enforcement of mandatory building regulations and standards. By establishing minimum standards for energy efficiency, water conservation, and interior environmental quality, these rules make sure that newly built homes and significant modifications adhere to predetermined sustainability standards. Governments employ financial incentives in addition to mandatory criteria to promote green building techniques. Incentives for building owners and developers who include sustainable design elements or obtain green building certifications could take the form of tax credits, grants, or subsidies. Governments can also impact the market by prioritizing green buildings for public projects through procurement laws. Governments may foster an atmosphere where green buildings are the standard rather than the exception and contribute to a more sustainable built environment for future generations by establishing clear guidelines, offering incentives, and setting an example. Queen, 2024, Emerging Trends in Green Architecture. Top emerging trends in sustainable architecture for 2024, building green. We've been seeing more and more instances of the emergence of sustainability in recent years. Numerous sectors and companies have begun to implement more environmentally friendly procedures and promote eco-friendly behaviors in their operations. In the case of architecture, too, building sectors and constructed environments have long been responsible for at least 39% of global carbon emissions. The number of eco-friendly structures, energy-efficient residences, and sustainable architecture has increased as 2024 draws to a close. This year, our blog will examine some of the new developments in sustainable architecture. Green architecture, also known as sustainable architecture, refers to the use of sustainable development techniques to produce livable spaces that are safe and healthy while reducing their detrimental effects on the environment. This can entail harming nearby ecosystems, wasting resources, or contributing to pollution. The modern methods used in the construction and general design of buildings are indicative of sustainable architecture. Often referred to as green architecture or even environmental architecture, sustainable architecture pushes architects to think creatively about how to use environmentally friendly materials, innovative technologies, and well-thought-out designs while minimizing environmental harm. Sustainable architecture is crucial for several reasons, including energy efficiency and environmental preservation. Sustainable development is gaining popularity due to our environmental harm, dependence on fossil fuels, and contribution to climate change. By incorporating sustainable practices into the design of living areas, residences, and housing projects, architects can satisfy client demands without depleting the resources of the environment. We may lessen our usage of the natural resources of the earth by building homes and living developments using environmentally friendly techniques. We are allowing our world to replenish itself by recycling, reusing, and transforming resources and existing spaces. We still have a long way to go, despite the fact that sustainability has recently gained more attention. Achieving sustainable architecture can take many different forms. Design. One of the most important aspects of developing sustainable home developments is the design. Whether designing a single residence or a complex of apartments, architects must carefully consider how to increase the sustainability of their designs. Using green architectural principles indicates that sustainability has been taken into account from the very beginning of the project. Water preservation. Sustainable construction development also heavily incorporates water-saving technology, which lessens the demand on natural resources and fresh water supplies. It is possible to use drought-resistant landscaping, rainwater collection, gray water recycling, and low-flow water systems. Architects are able to create structures with features that maximize water conservation, making them more sustainable. Recycling and waste reduction. When it comes to sustainable projects, material selection and deliberate waste reduction measures have a major impact. Utilizing low-emission and recycled materials reduces waste from the start, which means less waste ends up in landfills. Repurposed resources from buildings can be used in new construction. Building life cycle. Before these properties are built, life cycle assessments are yet another crucial architectural task that must be completed. Architects will conduct evaluations that take into account the materials used in construction, the way the property was constructed, and what will happen to the materials in the event that the structure is demolished or developed. Anonymous, 2024. Global Perspectives on Sustainable Building. Shifting viewpoints regarding green buildings. Some pictures come to mind when people consider fighting climate change: solar power plants taking the place of coal-burning power plants, trucks emitting pollutants being replaced by quiet electric cars, wide highways being converted into bike and pedestrian-only lanes. However, most individuals don't envision a building. They fail to recognize that buildings account for 1/3 of greenhouse gas emissions worldwide, meaning that making buildings greener can help mitigate climate change to a significant extent. Perhaps not. For this reason, the topic of this year's World Green Building Week, our yearly occasion to raise awareness, is centered on altering people's viewpoints. As an international organization dedicated to advancing green building globally, it is our responsibility to assist our local green building councils in pursuing the most critical facets of sustainability, as these will ultimately result in structures that not only reduce the environmental impact of buildings but also improve people's quality of life and well-being. And here's where we try to sway people's opinions even more. Furthermore, we think that by presenting compelling and frequently overlooked data, we may actually alter public perceptions of green buildings and encourage a closer bond between occupants and the environments they live in. Take the example of how occupant satisfaction in green buildings is 27% higher than in conventional ones. Or how studies have revealed that office workers who have windows get 46 minutes extra of sleep per night. Changing perspectives on green buildings. When people think about combating climate change, a few images come to mind: solar power plants replacing coal-burning power plants, silent electric cars replacing trucks that release pollutants, vast highways transformed to bike and pedestrian-only lanes. But most people don't picture a structure. They overlook the fact that buildings produce 1/3 of greenhouse gas emissions globally, which means that improving building sustainability can significantly slow down global warming. Anonymous, 2024. Glossary of terms. Important terminologies and definitions: building environment, places and constructions made by humans that serve as the backdrop for people's daily activities. This includes places to live, work, learn, travel, and have fun. Sustainable design is an architectural and construction methodology that prioritizes the use of eco-friendly materials and techniques to minimize environmental impacts, maximize resource efficiency, and improve occupant well-being. Equity-based approach, creating built environments with the needs of marginalized groups in mind, giving them priority, in order to ensure that they have equitable access to opportunities and resources. A field that integrates many disciplines, such as economics, urban planning, sociology, public policy, and environmental science, to offer a thorough comprehension of the built environment and its effects on society is known as an interdisciplinary area. The phenomenon known as the urban heat island, UHI, effect occurs when human activity and changes in land use, such as the increased use of concrete and asphalt, cause urban areas to experience greater temperatures than their rural surrounds. Life cycle assessment, LCA, is a methodical approach to assessing how a process or product will affect the environment at each stage of its life cycle, from extraction of raw materials to manufacture, use, and disposal. Green building certifications are uniform assessments that honor structures for their sustainable attributes, such as indoor environmental quality, water conservation, and energy efficiency. Building design techniques known as passive design strategies make the most of natural resources for lighting, heating, and cooling while lowering the need for mechanical systems. Rainfall harvesting is the process of gathering and holding onto rainfall in order to use it again, especially for flushing toilets and other non-potable applications like irrigation. The term biophilic design refers to an architectural style that enhances the built environment's natural aspects to foster residents' connection to the outdoors and overall well-being. Climate-responsive architecture, a design concept that uses material selection, strategic orientation, and passive design techniques to modify buildings to the climate conditions of the surrounding area, hence increasing energy efficiency and comfort. Smart building technologies are those that make use of automation, sensors, and Internet of Things, IoT, connectivity to optimize occupant experience, increase energy efficiency, and improve building performance. Introduction to Building and Environment, a complete guide overview of the built environment. This handbook delves into the complex interrelationships between human existence, health, and sustainability, and the built environment. Goals and Scope. The book's objective is to serve as an all-inclusive reference for construction and environmental professionals, students, and legislators. The intended readership for this work includes policymakers, architects, urban planners, environmental scientists, and students studying related subjects. Acknowledgements. Special thanks are extended to professionals and specialists whose ideas, experiences, and case studies enhance the information in this book. In summary, with a focus on the vital necessity of sustainability, creativity, and equality in our built environments, this thorough guide has successfully navigated the complexity of building and environmental design. We have looked at how buildings interact with their surroundings through a number of chapters, the value of sustainable practices, and the next steps that need to be taken to address urgent global issues like urbanization and climate change. Architects, planners, and legislators must adopt cutting-edge technologies, practice community-focused design, and give top priority to resilience against extreme weather occurrences going forward. The information contained in this handbook will help guide best practices and encourage everyone to take responsibility for creating constructed settings that promote environmental health and societal well-being. References 2023. AIA. Online available at https://www.aia.org/resource center/building life cycle assessment practice number :text equals the %20 output %20 of %20 and %20 LCA building %20 and %20 design %20 assessment %20 devices. Accessed for 8/2024. 2024. Planning Permission Ireland. Online available at https://planningpermissionireland.ie/multi-developments/3 Environmental Impact Assessments EIA and Strategic Environmental Assessments C/accessed 5/8/2024. A. Kakoskas, R.G., 2020. Science Direct. Online available at https://www.sciencedirect.com/topics/engineering/built environment number text equals the %20 build %20 environment %20 includes %20 human learn %2c %20 travel %2c %20 and %20 entertain. Access 308-2024. Anonymous, 2016. Industrial sector energy consumption. Online available at Chrome extension //www.eia.gov/outlook/IEO/PDF/industrial.pdf access 7/8/2024. Anonymous, 2020. ct.gov online available at https://portal.ct.gov/deep/waste management and disposal /construction and demolition waste /what is GWASTA number text equals construction %20 and %20 demolition %20, c %2060, %20 waste plaster %2c %20 metal %2c %20 and %20 asphalt. Access 12/8/2024. Anonymous, 2023. EPA. Online available at https://www.epa.gov/green/and/stormwater management practice CESPA facilities accessed 11/8/2024. Anonymous, 2023. Intel X Soft. Online available at https://www.intelxsoft.net/blog/8 emerging construction technology trends/accessed 15/8/2024. Anonymous, 2024. Business waste. Online available at https://www.businesswaste.co.uk/sectors/construction waste management/how to reduce waste in construction/access 12/8/2024. Anonymous, 2024. XM. Online available at https://www.xemic.com/articles/5 best practices for integrating renewable energy in commercial building design/access 7/8/2024. Anonymous, 2024. Elite Renewables. Online available at https://www.eliterenewables.co.uk/post/building green top emerging trends in sustainable architecture for 2024 access 21/8/2024. Anonymous, 2024. Graph. Online available at https://www.graph.info/engb/knowledge hub/blog/what is the difference between grey water recycling and rainwater harvesting.html number text equals grey water %20 recycling %20 and %20 rainwater %20 harvesting %20 are %20 both %20 efficient %20 methods %20 of their %20 applicability %20 in access 13/8/2024. Anonymous, 2024. Graph. Online available at https://www.graph.info/engb/knowledge-hub/blog/what is the difference between grey water recycling and rainwater harvesting.html number text equals grey water %20 recycling %20 and %20 rainwater %20 harvesting %20 are %20 both %20 efficient %20 methods %20 of their %20 applicability %20 in access 13/8/2024. Anonymous, 2024. NZABE. Online available at https://nzabe.in/knowledge-center/passive design/number text equals passive %20 design %20 strategies %20 aim %20 edit %20 glazing %2c %20 and %20 natural %20 ventilation. Access 13/8/2024. Anonymous, 2024. OCM. Online available at https://www.ucm.ac.uk/what's happening/article/smart buildings/number:\text equals smart %20 buildings %20 are %20 structures %20 that internet %20 of %20 things %20 IoT. Access 7/8/2024. Anonymous 2024. World Green Building Council. Online available at https://world.org/article/changing perspectives on green buildings/access 16/8/2024. Biro, S. 2024. Veolia. Online available at https://www.watertechnologies.com/handbook/chapter 02 Environmental Considerations accessed 12/8/2024. Castelli, K.R., 2021. Science Direct. Online available at https://www.science-direct.com/science/article/abs/pi/s09258574210025336 accessed 15/8/2024. Philae, S. 2024. Go Vocal. Online available at https://www.govocal.com/nuk/blog/community engagement local planning examples tips accessed 5/8/2024. Hammersmith, 2021. ACA Acoustics. Online available at https://www.acaacoustics.co.uk/uncategorized/acoustic considerations when developing residential buildings/accessed 11/8/2024. Heckard, MP, 2004. Science Direct. Online available at https://www.sciencedirect.com/topics/earth and planetary sciences/material life cycle access 6/8/2024. Henry, 2024. Constructive. Online available at https://constructivevoices.com/resilient design for climate change building for extreme weather events/number:\text equals building %24 20 extreme %20 weather %20 events climate %20 change %20 has and text equals utilize %20 materials %20 that %20 are %20 resistant are enforced %20 concrete %20 accessed 14/8/2024. Hoekstra, W. 2024. An official website of the European Union. Online available at https://transport.eceuropa.eu/transport theme/urban transport/sustainable urban mobility planning and monitoring _n number:\text equals a %20 sustainable %20 urban %20 mobility %20 plan %20 is %20 a %20 strategic %20 plan %20 designed a %20 better %20 quality %20 of %20 life. Accessed 15/8/2024. Holbert, C. 2024. CIM online available at https://www.cim.io/blog/building energy management systems BEMS accessed 8/8/2024. Ivana, 2024. Study Smarter. Online available at https://www.studysmarter.co.uk/explanation/environmental science/biological resources/sustainable water/number:\text equals strategies %24 20 reducing %20 water %20 waste collecting %20 rainwater %24 20 garden %20 use. Accessed 11/8/2024. Jacques, A. 2020. Novitr. Online available at https://www.novitr.com/blog/green building projects accessed 15/8/2024. Karthik, AP, 2024. The Architect's Diary. Online available at https://thearchitectsdiary.com/20 key factors and bonus insights for site selection /accessed 5/8/2024. Leach J.A. N. 2022. NIM. Online available at https://www.nspi.nlm.nih.gov/pmc/article/pmc7215772/accessed 8/2024. Leach J.A. NWBR. 2024. NIH. Online available at https://www.nspi.nlm.nih.gov/pmc/article/pmc7215772/accessed 9/8/2024. Lu. H. 2023. Reset Archgate. Online available at https://www.resetarchgate.net/publication/376875098_current_status_and_information_modeling_building_information_building_buildings accessed 3/8/2024. Luin. H. 2023. Online available at https://www.frontierson.org/journal/environmental science/article/10.3389/fens.2023.1107/full accessed 15/8/2024. M. Frunzak, P.W., 2011. Ecofon. Online available at https://www.ecofon.com/n/about-ecofon/functional demand/thermal comfort/access 10/8/2024. Morris, B. 2023. Construct and Commission. Online available at https://constructandcommission.com/lessons learned document with template/number:\text equals lessons %20 learned %20 form %20 part %20 of communication %2c %20 and %20 overall %20 project %20 performance. Accessed 15/8/2024. Park, L. 2022. Hutter Architects. Online available at https://hutterarchitects.com/the symbiotic relationship between buildings and the environment/accessed 3/8/2024. Patience, S. 2024. Green Spec. Online available at https://www.greenspec.co.uk/building-design/thermal mass/accessed 14/8/2024. Patry, P. 2021. Ultratech Cement. Online available at https://www.ultratechcement.com/for home builders/home building explain single/descriptive article/building materials used in construction number:\text equals their %20 are %20 various %20 kinds %20 of %2c %20 brick %20 blocks %2c %20 and %20 aggregate. Access 6/8/2024. Queen, Z. 2024. Reset Archgate. Online available at https://www.resetarchgate.net/publication/380207159_the_role_in_the_promoting_green_buildings accessed 15/8/2024. Reagan, M. 2024. EPA. Online available at https://www.epa.gov/heat islands/what you can do reduce heat islands accessed 15/8/2024. Reagan, 2024. Graph. Online available at https://www.grap.info/engb/knowledge hub/blog/ What is the difference between grey water recycling and rainwater harvesting? HTML text equals grey water %20 recycling %20 and %20 rainwater %20 harvesting %20 are %20 both %20 efficient %20 methods %20 of their %20 applicability %20 in accessed 11/8/2024. Reuters, T. 2024. Find law. Online available at https://www.findlaw.com/real estate/land-use-laws/land-use-and-zoning-basics.html accessed 5/8/2024. Samuel, N. 2024. Foyer. Online available at https://foyer.com/learn/sustainable architecture text equals basically %2c %20 sustainable %20 architecture %20 reduces %20 energy in %20 energy %20 and %20 environmental %20 design. Accessed 4/8/2024. Santiago Rodriguez, P. 2024. Hammad Global. Online available at https://hammondglobal.com/2024/02/12/5 Critical Challenges to Sustainable Development /accessed 15/8/2024. Sharma, P. 2023. Novitver. Online available at https://www.novitver.com/blog/passive design strategies and architecture text equals while %20 active %20 design %20 depends %20 on and %20 a %20 reduced %20 carbon %20 footprint. Access 7/8/2024. Sussman, 2024. Wikipedia. Online available at https://n.wikipedia.org/wiki/built_environment accessed 3/8/2024. SYST MES, D. 2024. Dassault System. Online available at https://www.3ds.com/sustainability/sustainable production/sustainable materials innovation accessed 6/8/2024. Tobias, M. 2024. Nearby Engineers. Online available at https://www.newyorkengineers.com/blog/introduction to resilient design text equals resilient %20 design %20 strategies resilience %20 is %20 not and text equals design %20 and %20 construct %20 buildings %22 and %20 other %20 extreme %20 weather %20 events. Accessed 4/8/2024. Vieira, S. 2023. WBDG. Online available at https://wbdg.org/resources/green building standards and certification systems accessed 4/8/2024. Vin Van Tran, DPAYC. L. 2020. NIH. Online available at https://www.inspi.nlm.nih.gov/pmc/article/pmc7215772/accessed 9/8/2024. Vin Van Tran, DPAYC. L. 2020. NIH. Online available at https://www.inspi.nlm.nih.gov/pmc/article/pmc7215772/accessed 10/8/2024. Zhong, W. 2022. Science Direct. Online available at https://www.science-direct.com/science/article/pi/s2095263521000479 accessed 11/8/2024.